In late October 2025, an interstellar object designated 3I Atlas passed within 29 million kilometers of the Sun, close enough that solar radiation should have vaporized surface ices, close enough that thermal models predicted observable outgassing within days, close enough that we could, for the first time, watch an object from another star system respond to our star's heat in real time. But thermal response in deep space bodies is not immediate. When sunlight strikes a comet nucleus kilometers thick, the energy doesn't just bounce back. It penetrates. It diffuses. It works its way through layers of dust, frozen gases, and carbonaceous material at speeds measured in centimeters per hour. Models predict delays of weeks to months between solar exposure and observable outgassing, rotation shifts, or spectral change. That delay window is closing now. Despite peak heating already passed, infrared emission from 3 Atlas increased instead of fading. Radio silence persisted longer than expected, then broke in patterns that shouldn't exist under standard comet models. The heat arrived on schedule. The response did not. This inversion, warming without cooling, silence without static, challenges every thermal lag model we validated on comets from our own solar system. And here's what makes this moment different from every other interstellar visitor we've tracked. Several instruments capable of resolving this anomaly are operating under time-compressed schedules, funding pressure, and shared mission priorities. The Very Large Array in New Mexico, the James Webb Space Telescope, the Atacama Large Millimeter Array in Chile. Each one pointed at dozens of targets, each observation window negotiated months in advance, each dataset filtered through committees that must balance discovery against budget. The universe doesn't wait for our administrative calendars. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. The data is still arriving. The models are still updating. And what we're learning about delay, about the time between cause and effect, between heat and response, might change how we understand not just interstellar objects, but the nature of matter itself when it travels between the stars. This is the delay between heat and response. This is not science fiction. This is December 2025. Chapter 1. October 14, 2025. The Physics of Waiting. Thermal lag is not a mystery. It is a feature of physics as fundamental as gravity, as predictable as orbital mechanics. When energy strikes matter, the response unfolds at speeds dictated by thermal conductivity, material density, and the geometry of heat diffusion. In celestial bodies, comets, asteroids, Kuiper belt objects, this delay is not measured in seconds or minutes. It is measured in weeks, sometimes months. On October 14, 2025, scientists at the Jet Propulsion Laboratory in Pasadena gathered to review the first post-perihelion datasets from 3 Atlas. The object had reached its closest approach to the Sun 3 days earlier, swinging through a region of space where solar flux exceeds 1,300 watts per square meter. Enough to sublimate water ice. Enough to trigger the explosive release of carbon monoxide, carbon dioxide, and methane from subsurface pockets. Enough, in every model tested against comets from our own solar system, to produce an observable coma within 72 hours. The data showed no coma. Dr. Yuki Tanaka, a planetary scientist specializing in cometary thermophysics, pulled up a simulation on the main display. The model showed 3 Atlas as a rotating ellipsoid roughly 800 meters along its longest axis. Its surface a patchwork of light-absorbing organics and reflective ices. As simulated sunlight struck the dayside, surface temperatures climbed past 200 Kelvin. Subsurface layers, insulated by dust and porous structure, warmed more slowly. The thermal wave propagated inward at approximately 2 centimeters per hour. Heat doesn't teleport, Tanaka said, gesturing to the color-coded cross-section. It conducts. It radiates. It diffuses through material that's barely denser than cigarette ash in some regions. If you want subsurface ices to sublimate, you have to wait for the heat to reach them. The room was quiet, except for the hum of cooling fans, and the occasional scrape of a chair. These were people who understood waiting, who had spent careers watching pixels resolve into moons, spectra sharpen into chemical fingerprints, thermal curves reveal the hidden architecture of worlds. But waiting requires a framework, a prediction, a sense of how long eventually will take. For comets originating in our solar system, that framework is robust. Comet 67P, Churyumov-Gerasimenko, studied in exhaustive detail by the Rosetta mission, showed a thermal lag of approximately 6 weeks between perihelion and peak outgassing. Comet Hale-Bopp exhibited delays of up to 8 weeks, with different volatile species responding on different timescales. Water ice, with its high latent heat of sublimation, responded last. Carbon monoxide, volatile at much lower temperatures, responded first. The pattern was consistent, predictable, quantifiable. 3I Atlas had been expected to follow the same pattern, adjusted for its interstellar origin. Models accounted for potentially different ice mixtures, altered by exposure to cosmic rays during millennia in interstellar space. They accounted for higher porosity, lower albedo, compositional layering. The prediction window ranged from 3 to 7 weeks post-perihelion for observable outgassing. October 14th was day 3. Too early to worry. Too early to call the silence anomalous. But the infrared data was already strange. Dr. Ravi Chandra, an astrophysicist on loan from the Indian Space Research Organization, highlighted a section of the thermal emission curve. "We're seeing elevated mid-infrared output at 8 microns, he said, consistent with silicate dust warm to approximately 250 Kelvin, but the spatial distribution is wrong." On the display, a false color map showed 3I Atlas glowing unevenly. The warmest regions were not concentrated on the subsolar point, the area receiving the most direct sunlight, but spread across the limb, the transitional zone between day and night. "Heat's migrating," Chandra continued, conducting through the interior, re-radiating from areas that should be cooling by now. Tanaka leaned forward. "Lateral heat flow. That's not unusual in low conductivity material. But the magnitude is higher than predicted." "By how much?" 15%, maybe 20, depending on albedo assumptions. A murmur passed through the room. 15% was not catastrophic. It was not paradigm-breaking. It was the kind of discrepancy that could mean a dozen things: slightly different material properties, an unexpectedly smooth surface, a rotation axis tilted differently than estimated. Or it could mean the models were missing something. "Do we have spectral resolution on the warm zones?" asked Dr. Alina Popescu, a data analyst who had spent the last 18 months refining photometric techniques for faint, fast-moving objects. Chandra shook his head. "Not yet. We're at the limit of spatial resolution for ground-based infrared. Webb could resolve it, but we're not scheduled for another observation window until November 2nd. Not barman. 3 weeks, Popescu said quietly. 3 weeks. Chandra confirmed. In the silence that followed, someone made coffee. Someone else updated a spreadsheet tracking observation requests across 6 telescopes and 4 continents. The work continued, because the work always continued. Data arrived, was processed, was archived. Questions were logged. Models were adjusted. Plans were made for follow-up observations. But beneath the routine, a different kind of waiting had begun. Because thermal lag, while predictable in principle, is sensitive to variables we cannot directly observe. Porosity, composition, thermal conductivity. These properties are inferred from indirect measurements. Brightness, spectral lines, thermal emission, and those measurements carry uncertainties. A 15% discrepancy could evaporate with better data. Or it could grow. The data doesn't rush. It waits. That night, Tanaka remained in the lab, after the others had left, reviewing Rosetta data from Comet 67P. She pulled up thermal maps from the weeks following perihelion, watching the heat soak through the nucleus in time-lapse. The progression was smooth, orderly, each layer warming in sequence, each volatile species responding when its temperature threshold was crossed. She opened a second window and loaded the preliminary 3E Atlas thermal model. Same basic physics, same diffusion equations, Same boundary conditions. But the curves didn't quite match. The interstellar object was retaining heat longer than expected, releasing it more slowly, redistributing it more efficiently. Not by a lot. Not enough to violate any physical laws, but enough to sit uncomfortably at the edge of the uncertainty margins. Tanaka saved the comparison and flagged it for discussion at the next team meeting. Then she closed her laptop, turned off the lights, and walked out into the Pasadena night where the air was cool and the stars were dimmed by city glow. Somewhere out there, 29 million kilometers sunward and receding, 3i Atlas continued its silent thermal negotiation with the sun. Heat flowed inward through porous ice and carbon-rich dust. Molecules vibrated faster. Chemical bonds strained. Energy accumulated in subsurface layers too deep for our instruments to see directly. And the waiting continued. Because in space, cause and effect are separated not just by distance, but by time. Light takes 8 minutes to travel from the sun to Earth, but heat takes weeks to travel 800 meters through a comet's heart. We see the flash. We wait for the thunder. And sometimes, the thunder sounds different than we expect. On October 14th, the models predicted eventual outgassing. The data showed thermal anomalies. And the distance between those two observations, between what should happen and what was happening, defined a space where understanding had not yet arrived. The physics of waiting is also the physics of uncertainty. And uncertainty, given time, can become its own kind of answer. Chapter 2. October 18, 2025, when 3i Atlas didn't cool down. 4 days later, the infrared anomaly had not resolved. It had intensified. Mid-infrared observations from the Gemini North Telescope on Mauna Kea showed 3i Atlas radiating more energy than it had on October 14. Not slightly more. 22% more, despite moving farther from the sun, despite receiving less solar flux with each passing hour. This should not happen. When a body moves away from a heat source, it cools. Not instantly. Thermal inertia provides lag, but cooling begins immediately. The surface radiates energy into space faster than sunlight can replace it. Subsurface layers, still warm from earlier heating, conduct energy outward toward the cooling surface. The entire system trends toward equilibrium with the colder environment. 3i Atlas was not trending toward equilibrium. It was heating up post-perihelion. Dr. Ravi Chandra stood before a wall-mounted display in the JPL Situation Room, cycling through thermal maps captured at 6-hour intervals. Each image showed the object as a fuzzy, color-coded blob, red for warm, blue for cool, rotating slowly against the black of space. Over the sequence, the red zones expanded. Not dramatically, not explosively, but unmistakably. Energy is being released from subsurface reservoirs, Chandra said. Delayed sublimation of volatiles that took days to heat up. That part makes sense. He paused. What doesn't make sense is the rate. Dr. Yuki Tanaka pulled up a graph comparing observed thermal output against 3 model scenarios. The blue line represented a standard comet model with high porosity and low thermal conductivity, the fluffy snowball scenario. The green line represented a denser, more consolidated object with higher heat retention. The red line represented 3i Atlas. The red line sat above both predictions. Could be compositional, suggested Dr. Alina Popescu, zooming in on the spectral data. If there's a higher concentration of supervolatiles, carbon monoxide, methane, they'd sublimate at lower temperatures, earlier, more energetically. We checked for that, Tanaka replied. Carbon monoxide emission lines are present, but weak. Consistent with a few percent by mass, not enough to explain this level of thermal output. What about an insulating layer? Asked Marcus Delgado, an engineer who'd worked on the Rosetta lander and understood how thin layers of dust could dramatically alter heat flow. If the surface sealed up as ice is sublimated, you could trap heat underneath, build pressure, delay release. Chandra nodded slowly. Possible. But we'd expect to see that heat eventually break through in discrete venting events. Sharp temperature spikes. Instead, we're seeing sustained, diffuse emission. Shamnom, the room fell quiet. On the screen, 3, Atlas glowed persistently, a red smudge defying thermal logic. Heat doesn't disappear, Delgado said finally. If it's radiating more than it's receiving, it has to be coming from somewhere. Internal heat source? Popescu offered, then immediately shook her head. No. Radioactive decay would have been radiating continuously, not just post-perihelion. And we'd see it in the pre-perihelion baseline. Exothermic chemistry? Tanaka said. Water rock reactions maybe. Some asteroids showed transient thermal events from aqueous alteration. Chandra pulled up a paper on his tablet, one he'd been reading on the flight from Bangalore 2 weeks earlier. There's precedent. Sirius showed unexpected bright spots that might be linked to subsurface brine migration. Enceladus has its geysers, but those are worlds with significant internal structure. 3I, Atlas is 800 meters across. Small things can be warm, Delgado countered. Bennu had hotspots. Ryugu had thermal anomalies. Sure, but those were explained by surface roughness, shadowing effects, differences in albedo. This. Chandra gestured to the graph where the red line continued its stubborn ascent. This is a bulk thermal property. The whole object is behaving like a battery that charged up during perihelion and is now discharging slower than it charged. The analogy hung in the air, imperfect, but evocative. Because that's what the data suggested. Not a passive response to solar heating, but an active redistribution. Energy flowing through the interior, not by simple conduction, but through some process that moved heat more efficiently than porous ice should allow. Phase change was the obvious candidate. Ice absorbing energy as it transitioned to gas migrating through pore spaces, recondensing in cooler regions, releasing that energy deeper in the nucleus. A heat pipe effect, well understood in engineering, occasionally invoked in cometary science. But heat pipes required temperature gradients. They required volatiles to move down gradient, from warm to cold. 3 Atlas was releasing heat uniformly, not concentrating it. Maybe we're thinking about this wrong, Popescu said. She stood and walked to the whiteboard, picking up a marker. We keep treating this like a comet. But what if it's not? She drew a simple circle. What if it's mostly rock? Dense core. Thin ice mantle. Rock heats up slower, but retains heat longer. Release gets delayed because you're waiting for conduction through high-density material. Tanaka considered. Possible. But the albedo's too high. Reflectance suggests significant ice content, at least on the surface. Then a hybrid. Popescu continued, adding layers to her diagram. Rocky core, icy shell, but thermally connected. Ice sublimates, exposes rock radiates stored heat. That'd give you sustained emission without visible outgassing. Chandra ran the numbers quickly on his tablet. You'd need about 30 to 40% rock by volume to store that much heat. That'd make 3I Atlas denser than most Kuiper belt objects. Way denser than most solar system comets, Tanaka clarified. We don't have statistics on interstellar object densities, sample size of 2, and Oumuamua never got close enough for detailed thermal analysis. The conversation spiraled through possibilities, each one plausible in isolation, each one straining slightly when matched against the full dataset. Too much heat for pure ice, too uniform for heterogeneous composition, too delayed for simple thermal lag. What if the heat is being redistributed, not released? The question surfaced first as a murmur, then as something spoken aloud. No one could identify who said it first, but once articulated, it settled over the room like a change in air pressure. Redistribution implied process, implied mechanism, implied that 3I Atlas was doing something with the energy, not just absorbing and radiating it passively. We need better spatial resolution, Chandra said finally. If different regions are warming at different rates, if there's directional heat flow, we need to map it. Tanaka checked the observing schedule. Webb's next window is November 2nd. ALMA could give us submillimeter observations before that, but they're booked until October 28th. 10 days, Popescu calculated. 10 days, Tanaka confirmed. Outside, the California evening deepened toward night. The Jet Propulsion Laboratory, perched in the foothills above Pasadena, glowed with the lights of people working late, working weekend shifts, working because the universe had presented a question, and questions demand answers, even when answers are slow to arrive. Somewhere in the space between Earth and the Sun, 3I Atlas continued its inexplicable warming. Infrared photons streamed away from its surface at the speed of light, carrying energy that should have dissipated days ago. Radio telescopes, not yet pointed its direction, listened to other targets. Spectroscopes resolved other spectra. The observational apparatus of planetary science, vast but finite, turned its attention according to schedules made months ago. And in the gap between observation windows, 3 Atlas evolved unseen. The data doesn't rush. It waits. That night, Ravi Chandra couldn't sleep. He lay in his hotel room near the JPL campus, watching the digital clock count minutes, thinking about heat and time, about the way energy moves through matter, about the difference between what models predict and what nature provides. In graduate school, he'd studied the thermophysics of asteroid regolith, learning how grain size and packing density affected thermal inertia. He'd learned that a few centimeters of dust could insulate like meters of rock. That surface roughness could create thermal environments varying by 100 degrees across millimeters. That predicting temperature required knowing not just composition, but architecture. 3I Atlas had architecture we couldn't see. Structure hidden beneath a surface we could barely resolve. And that structure was responding to solar heating in ways that brushed against the edges of every model we'd validated. He picked up his phone and opened the thermal dataset again, scrolling through the temperature curves. The warmth persisted, spread, refused to fade according to the expected exponential decay. Somewhere in those curves was an explanation. A physical process obeying physical laws, even if those laws manifested in unexpected combinations. The alternative, that the object was somehow actively managing its thermal state, was not something his training allowed him to seriously entertain. Not yet. Not on October 18th, 25, when the data was still sparse, the observation windows still opening, the models still adjusting. But the thought arrived anyway, unbidden and uncomfortable. What if we're not just watching an object cool down? What if we're watching it do something? He set the phone aside and closed his eyes, listening to the distant hum of Los Angeles traffic, waiting for sleep that would be slow to come. Chapter 3. October 22nd, 25. The telescopes that almost missed it. The observation gap began on October 20th, and was not scheduled to close until October 28th. 8 days. In the lifespan of a solar system, in the orbital period of galaxies, in the slow collapse of star-forming nebulae, 8 days is nothing. A rounding error. A pause between breaths. But 3I Atlas was changing on a timescale of hours, and 8 days without new data meant 8 days of evolution unrecorded, of thermal processes progressing unseen, of potential outgassing events, or spectral shifts, or rotational changes lost to the scheduling constraints of Earth-based astronomy. This was not negligence. It was logistics. Dr. Alina Popescu sat in her office at JPL, reviewing the observing calendar for every major telescope capable of contributing to the 3I Atlas investigation. The James Webb Space Telescope, booked for a high redshift galaxy survey through October 30th. The Atacama Large Millimeter Array in Chile, undergoing maintenance on 3 of its 66 antennas operating at reduced capacity. The Very Large Array in New Mexico, pointed at a pulsar timing array, part of a multi-year gravitational wave detection effort that couldn't be interrupted without jeopardizing years of baseline data. Each facility operated under a peer-reviewed time allocation system, where observing proposals were submitted months in advance, evaluated by committees, ranked by scientific priority. The process was designed to be fair, transparent, and resistant to favoritism. It was also glacially slow, when measured against astronomical events that unfolded in days. Popescu had submitted a director's discretionary time request for Webb on October 16th, arguing that the thermal anomaly constituted a time-sensitive target warranting schedule disruption. The request was still under review. Even if approved, it would take 48 hours to reconfigure the telescope's observation plan, upload new pointing instructions, and execute the observation. She opened an email from the DDT review panel. Request acknowledged. Committee meeting scheduled for October 24th. Notification within 72 hours. October 24th. 3 days away. Then 72 hours more for notification. Then, if approved, 2 days for implementation. By then, it would be November. She leaned back in her chair, staring at the ceiling tiles, thinking about the gap between scientific urgency and institutional process. Both were necessary. Both were rational. And both, occasionally, produced outcomes where time-sensitive phenomena went unmonitored because the systems designed to study them could not adapt fast enough. Across the campus, Dr. Marcus Delgado was having a different version of the same conversation. He stood in the Mission Operations Center, phone pressed to his ear, talking to a colleague at the European Southern Observatory in Garching, Germany. I understand the sphere instrument is optimized for exoplanet imaging, but the adaptive optics system could resolve surface features on 3I Atlas that we can't get any other way, Delgado said, keeping his voice level despite the frustration building behind his sternum. The voice on the other end was sympathetic but firm. Marcus, you know how this works. Sphere is booked through November 15th. We have doctoral students whose thesis data depends on those observations. We can't just bump them for a target of opportunity. This isn't a normal 2. It's an interstellar object exhibiting anomalous thermal behavior during the narrowest observational window we'll ever have. I know, and if you'd submitted a regular proposal during the last cycle, you'd have time allocated. But DDT requests have to meet a very high bar. Supernova gamma ray burst, something with a decay timescale measured in hours. This might have a timescale of days. We're seeing thermal output increase post-perihelion, which shouldn't be happening. That gap between heating and response is interesting, genuinely interesting, but it's not an emergency in the sense that ESO policy defines emergency. Delgado thanked him, ended the call, and stared at the wall of mission patches behind the operations desk. Rosetta, Dush, Cassini.Orstein. New Horizons. Decades-long missions with billion-dollar budgets, each one a testament to what humanity could achieve when we pointed our instruments at something and kept them pointed long enough to understand it. 3. Atlas would be observable for another 6 weeks, maybe 8 if it remained bright enough. Then it would recede beyond the sensitivity threshold of all but the largest telescopes, becoming a speck indistinguishable from 1,000 other faint objects, its moment of solar awakening. If that's what this was, over before we'd fully documented it. The resource allocation problem was not unique to 3I Atlas. Every field of astronomy faced it. Gravitational wave detectors balanced sensitivity calibrations against observation time. Planetary missions chose between extended operations at one target or repositioning for another. The Hubble Space Telescope, even in its twilight years, received 10 times more observing proposals than it could accommodate. The universe was full of interesting things. Our instruments were finite. But 3. Atlas wasn't just interesting. It was the third confirmed interstellar object ever detected, the first to pass close enough to the Sun for detailed thermal studies, and the only one exhibiting behavior that strained our cometary models. It was, in a very real sense, a sample of another stellar system delivered to our doorstep for free, asking only that we pay attention. And we were struggling to pay attention because the systems we'd built to organize our attention were optimized for the expected, not the anomalous. Dr. Yuki Tanaka joined Delgado in the operations center, carrying a printout of the thermal emission data. I talked to the team at Subaru Telescope, she said. They can give us 4 hours on October 26th if weather holds. Mid-infrared imaging, not spectroscopy, but it's something. 4 hours, Delgado repeated. Better than nothing. Better than nothing, Tanaka agreed. They stood together in silence, watching the mission clock count seconds. Somewhere in the budget offices, funding requests for the next fiscal year were being evaluated. Somewhere in conference rooms, committees debated the scientific merit of proposed observations. Somewhere in the complex machinery of institutional science, People made reasonable decisions that added up to an unreasonable outcome. An interstellar visitor, warming mysteriously, observed in fragments. The phone on the operations desk rang. Delgado answered it, listened, nodded. Understood. Thank you for checking. He hung up. Vela can give us 6 hours on November 1st. Radio continuum observations. Ninagro. Kinyamund. Tanaka marked it on her calendar. That's 10 days from now. 10 days from now, Delgado confirmed. The gap yawned before them. Not a failure of science, but a feature of systems designed for different timescales. Telescope, time allocated in 6-month blocks. Budgets planned in annual cycles. Careers, built on decade-long projects. 3 Atlas operated on no one's schedule but physics. That afternoon, Popescu drafted an email to the International Astronomical Union's Central Bureau for astronomical telegrams, alerting the broader community to the thermal anomaly and encouraging additional observations. Within hours, responses arrived from amateur astronomers, university groups, and international collaborators. A team in South Africa could contribute optical photometry. A radio telescope in Australia could attempt long-wavelength detection. A graduate student in Tokyo had archival spectroscopic data from October 10th that might provide pre-perihelion baseline. The community mobilized not because funding had been allocated or committees had met, but because someone had asked. Because science, at its core, was still a collective effort where individuals with access to instruments pointed them at interesting things. But coordinating those observations, standardizing the data, ensuring compatibility between different instruments and analysis pipelines, that took time. The kind of time that 3A Atlas, receding from the Sun at 23 kilometers per second, did not necessarily provide. On October 22nd, the object was 32 million kilometers from the Sun and moving outward. Its surface temperature, inferred from infrared emission, remained elevated at approximately 240 Kelvin. No optical coma had been detected. No spectral lines indicating active outgassing had appeared. The thermal anomaly persisted, documented by a handful of observations separated by days, each one a snapshot of a process unfolding in the gaps between snapshots. Human systems, schedules, budgets, committee reviews struggled to keep pace with interstellar timelines. And in that struggle, in the friction between what we wanted to observe and what our systems allowed us to observe, a different kind of delay emerged. Not the thermal lag of heat diffusing through matter, but the institutional lag of attention diffusing through bureaucracy. Both were real. Both were measurable. Both, in their own way, defined what we could know and when we could know it. The data doesn't rush. It waits. But waiting, in astronomy, is rarely passive. While telescopes remain pointed elsewhere, analysts work through existing data, refining thermal models, extracting every signal from every photon captured during earlier observations. Spectra were reprocessed with updated calibrations. Light curves were analyzed for periodic variations. Orbital parameters were refined, using astrometric measurements from amateur observers. The work continued, because the work always continued. Because even when new observations were delayed, old observations still held information waiting to be found. And because somewhere in those refined models, in those recalibrated spectra, in the gap between what was measured and what was predicted, an answer was forming. Slowly. Incrementally. Like heat diffusing through a comet's heart. Chapter 4. October 26, 2025. A signal that arrived late. The radio emission was first detected at 3:47 Universal Time by the Parkes Observatory in New South Wales, Australia. Not a beacon, not a pattern, just a faint, broadband hiss emerging from the coordinates of 3 Atlas, lasting 11 minutes before fading below the detection threshold of the 64-meter dish. Dr. Colin Marsh, the radio astronomer on duty, almost dismissed it. The signal strength was marginal, barely 3 sigma above the noise floor, and transient radio sources were common. Terrestrial interference. Satellite glint. Background pulsars. The sky was full of radio noise masquerading as signal. But the frequency distribution was unusual. Not the narrow spike of a pulsar. Not the broadband roar of a magnetar. Something in between. Power concentrated between 1.4 and 1.7 GHz, declining smoothly toward higher and lower frequencies, peaking at approximately 1.5 GHz, with no fine structure, no modulation, no obvious periodicity. It looked natural. It looked like thermal emission from hot plasma, or synchrotron radiation, from relativistic electrons spiraling through magnetic fields. Except 3, Atlas wasn't hot enough to produce plasma radiation, and it had no magnetic field capable of accelerating electrons to relativistic speeds. Marsh flagged the detection and sent a notification to the International Astronomical Union's transient name server, along with a copy to the JPL team tracking 3 Atlas. Then he returned to his scheduled observations, pointing Parkes at a distant quasar, leaving 3 Atlas to whatever quiet mystery it was enacting 33 million kilometers away. 8 hours later, Dr. Ravi Chandra saw the notification while reviewing his morning emails. He read it twice, checked the reported coordinates, confirmed they matched 3I Atlas's predicted position to within the uncertainty of Parkes's beam width. Then he opened the raw data file and looked at the spectrum. It was cleaner than he expected. Smooth. Almost featureless. The kind of spectrum that emerged from optically thin thermal emission, or from processes so well averaged over time that all the fine details blurred into a continuum. He ran a quick calculation. If the emission was thermal, the brightness temperature would be approximately 40,000 Kelvin. Far too hot for sublimating ice. Far too hot for anything happening on a comet's surface. If the emission was non-thermal, it required a mechanism. Shock-heated gas from an outburst. Lightning in a dusty coma. Magnetic reconnection, if 3I Atlas somehow had a transient magnetic field generated by what? Charged dust? Ionized gas. Every explanation required something that shouldn't exist on a small, inert, interstellar object. Chandra forwarded the data to Dr. Yuki Tanaka and Dr. Alina Popescu with a one-sentence message. This shouldn't be possible. 20 minutes later, all 3 were on a video call, the radio spectrum displayed across their screens. Could it be interference? Popescu asked, playing devil's advocate. Satellite downlink, military radar, something terrestrial? Marsh, patched in from Parkes, shook his head. We checked. No known satellites in the beam. No scheduled radar operations in that frequency band. And the source moved with 3 Atlas across the sky, tracked with the object's motion for the full 11 minutes. Did you get follow-up? Tanaka asked. Tried. Reobserved the coordinates 90 minutes later. Nothing. Nothing. Observed again at the next available slot. 4 hours after the original detection. Still nothing. Was intentellanch? Chandra leaned back, processing. So we have an 11-minute radio transient, coincident with 3I Atlas, no repetition, no obvious terrestrial source. Correct, Marsh confirmed. And the spectrum is smooth, broadband, centered at 1.5 GHz. Correct, Dite. What's the probability this is a random background transient that just happened to align with our target? Marsh had already run the numbers. Parkes detects about 20 transient radio sources per year in our survey work. That's roughly 1 per 18 days. But most are much narrower in frequency or show clear modulation. For a broadband continuum transient like this, rate drops to maybe 2 or 3 per year. So roughly 1 in 100 days, Popescu calculated. Right. And the sky's 41,000 square degrees. Parkes's beam at 1.5 GHz is about 14 arc minutes, so 0.01 square degrees. Odds that a random transient appears in that specific patch of sky during an 11-minute observation. Chandra finished the calculation. 1 in 20,000. Silence filled the video call, broken only by the faint hiss of audio compression and someone's cat meowing in the background. Not impossible, Tanaka said finally, but uncomfortable. Very uncomfortable, Popescu agreed. Marsh cleared his throat. There's one other thing, the timing. He pulled up a timeline showing 3 Atlas's thermal evolution alongside the radio detection. The object had been warming post-perihelion for 8 days, infrared emission increasing steadily. The radio transient occurred approximately 5 hours after the most recent infrared observation had shown a slight plateau in the warming curve. Not a decrease, but a leveling off, as if the thermal output had reached some temporary equilibrium. Could be coincidence, Marsh said. Or it could be related. If you had a subsurface volatile pocket that suddenly vented, you might get a brief outburst of gas and dust. That could produce radio emission if the gas was ionized. Ionized by what? Chandra asked. Ultraviolet from the sun, triboelectric charging in the dust, even cosmic rays if the gas expanded into a low-density cloud. Tanaka pulled up a paper on cometary radio emission from the SA archives. There's precedent. Kontali produced weak radio emission during its 1986 apparition, attributed to ion-electron collisions in the coma. But that was continuous, not a transient. No. And Halley had a massive coma, Popescu added. Orders of magnitude more gas than we've detected from 3 Atlas. If this was an ionized outburst, it'd have to be incredibly efficient. Nearly all the gas ionized, radiating in a narrow frequency range. Chandra did the energy calculation. For 11 minutes of radio emission at the observed flux density, the total energy output was approximately 10 to the 13th joules, equivalent to the kinetic energy of about 200 kilograms of gas, ejected at 1 kilometer per second. Not impossible. Small outbursts of that scale happened on comets. But 3I Atlas hadn't shown any optical evidence of outgassing. No coma. No brightening. No spectral lines indicating gas release. We need more data, Tanaka said, which was both true and frustratingly obvious. Laws available November 1st, Chandra reminded them. 6-hour observation window. We can set up multiple frequency bands, look for repeat transients, map any extended emission. 6 days, Popescu calculated. 6 days, Chandra confirmed. The call ended with assignments distributed. Marsh would continue monitoring with Parks whenever scheduling allowed. Chandra would coordinate the Viale observation, designing a frequency strategy optimized for detecting weak transients. Tanaka would review the infrared data for any correlations with the radio detection time. Popescu would search archival radio surveys for any previous transient detections in the same region of sky. Each task was actionable. Each one advanced understanding incrementally. But none provided immediate answers. That evening, Chandra stayed late at JPL, replaying the radio spectrum on his monitor. The smooth curve rose and fell across the frequency axis, elegant and inexplicable. It looked like noise. It looked like signal. It looked like something natural, producing a signature we didn't quite understand. He thought about lightning on Jupiter, radio bursts from auroras, emissions from the magnetospheres of distant exoplanets. Nature had 1,000 ways to produce radio waves. Most were well understood. Some were still mysterious. But all required energy sources, power supplies, mechanisms. 3I Atlas was a cold rock, tumbling through space, warmed briefly by the sun, now cooling as it receded back into the darkness between stars. What mechanism could produce 40,000 Kelvin brightness temperatures in an object that should barely reach 300 Kelvin? Sublimation shock, electric discharge, magnetic reconnection. Each possibility strained against the constraints of size, temperature, composition. Or maybe the constraints were wrong. Maybe interstellar objects carried properties that solar system comets didn't. Maybe cosmic ray bombardment over millions of years altered their chemistry in ways that enabled transient radio emission. Maybe the porous structure created charge separation that discharged suddenly when triggered by thermal expansion. Maybe. The word hung in the air like the radio signal itself. Faint, transient, refusing to resolve into certainty. Chandra saved his notes and shut down his workstation. Outside, the lights of Pasadena spread across the valley, a constellation of human activity glowing against the night. Somewhere above, invisible through city haze and atmospheric glow, 3 Atlas continued its silent journey, carrying questions we'd only begun to articulate. The data doesn't rush. It waits. But waiting now felt different, because the data had changed. A new dimension had appeared. Radio emission, where none should exist. An 11-minute whisper, at frequencies we'd barely thought to check. And the distance between that whisper and silence, between signal and noise, between detection and dismissal, was measured not in kilohertz or signal strength, but in the statistical likelihood of coincidence. 1 in 20,000. Low probability. High impact. The kind of odds that made scientists uncomfortable, that turned probably noise into probably natural. But let's keep watching. Because probably was not proof. And probably, given time, could become something else entirely. Chapter 5. October 30th, 2025. While 3I, Atlas puzzled astronomers in near-Earth space, Mars offered a lesson in patience 57 million kilometers away. The Perseverance rover had been exploring Jezero crater since February 2021, collecting rock samples, analyzing mineral composition, searching for chemical signatures of ancient microbial life in a landscape that had been lakefront real estate 3.5 billion years ago. The work was slow by human standards. Months to traverse kilometers, weeks to select a sampling site, days to drill into rock and analyze the powder inside. But on October 30th, 2025, a paper appeared in Nature Geoscience that made the slowness make sense. Dr. Lina Torres, a geochemist at Caltech, was its lead author. The paper's title, Delayed Aqueous Alteration Chemistry in Martian Regolith. Evidence from Pixel and Sherlock. The finding was technical but profound. Chemical reactions in Martian rock didn't happen immediately when water was introduced. They happened slowly, over weeks, as water molecules worked their way through grain boundaries and mineral defects, breaking bonds, rearranging atoms, leaving signatures that appeared not during the wetting event itself, but long after. The Perseverance instruments, Pixel, an X-ray fluorescence spectrometer, and Sherlock, a Raman spectroscope, had detected mineral phases that formed only in the presence of liquid water. But those phases appeared in layers suggesting formation occurred weeks or months after the initial aqueous event, when water should have long since evaporated in Mars's thin, dry atmosphere. The implication: water could persist in tiny pockets within porous rock, protected from evaporation, reacting slowly with surrounding mineral. Delayed chemistry. Delayed alteration. Response separated from stimulus by timescales, long enough to obscure the connection between cause and effect. Dr. Ravichandra read the paper on his tablet over breakfast, alone in his hotel room near JPL, eating microwaved oatmeal and drinking coffee that had gone lukewarm. He read it not because he was a geochemist. He wasn't, but because delay had become the theme of his October, and here was Mars confirming what 3Atlas had been demonstrating. Matter responds to energy on its own schedule, not ours. He bookmarked the paper and sent the link to Dr. Yuki Tanaka with a subject line, "Delay is not anomalous." Tanaka replied 15 minutes later, "Delay is normal. This much delay is not." She was right, of course. Mars's delayed chemistry unfolded over weeks because water diffusion through rock is slow. 3Atlas's thermal lag should unfold over weeks because heat diffusion through porous ice is slow. Both delays were predictable from first principles. But 3Atlas was showing delays that exceeded predictions. Heat lingering too long. Radio emission arriving late. A thermal response curve that should have peaked and declined, but instead plateaued and persisted. Chandra thought about the Mars paper while showering, while driving to JPL, while walking across the campus toward the Situation Room where the team had scheduled a morning briefing. The analogy wasn't perfect. Mars was a planet. 3Atlas was a kilometer-scale object. Mars had liquid water. 3Atlas had frozen volatiles. But the principle held. Delay is how matter negotiates change. It's not a bug. It's a feature. The briefing room was fuller than usual. Word of the radio transient had spread through the planetary science community, drawing interest from researchers whose primary focus was elsewhere, but who recognized that anomalous data, wherever it appeared, often taught something new. Dr. Marcus Delgado was there, along with Dr. Alina Popescu, Tanaka, and half a dozen others whose names Chandra was still learning. Grad students, postdocs, visiting scientists from international collaborators. Tanaka stood at the front of the room, pulling up a comparison slide. Mars geochemistry on the left, 3I Atlas thermal evolution on the right. Both systems show delayed response, she began. Mars shows mineral alteration weeks after water exposure. 3. Atlas shows thermal emission weeks after solar heating. The difference is that Mars's delay is fully explained by diffusion-limited chemistry. 3. Atlas's delay is not fully explained by thermal diffusion. She clicked to the next slide, a graph showing observed thermal output versus predicted thermal output, the gap between them widening with each passing day. We're now 12 days post-perihelion. Thermal models predict we should be seeing exponential decay in infrared emission. Instead, we're seeing sustained output at 85% of peak. That's not impossible. Thermal inertia, insulating layers, subsurface heat reservoirs can all extend the cooling time. But the magnitude is outside the 1 sigma uncertainty range of our models. Could it be compositional? Someone asked from the back. Higher fraction of refractory organics, lower albedo, more efficient absorption? Tanaka nodded. Possible. We're refining models to account for that. But even with aggressive assumptions about composition, we're still over-predicting the cooling rate. Active sublimation? Suggested a grad student with a NASA lanyard. If volatiles are venting, latent heat absorption would slow cooling. We'd expect to see gas emission lines, Popescu interjected. Spectroscopy's been clean. No CO, no CN, no O. Either there's no sublimation, or it's happening at rates below our detection threshold. Delgado leaned forward. What about the Mars analogy? If delayed chemistry can happen in rock, could delayed sublimation happen in ice? Tanaka considered. In principle, yes. If you have ice trapped in a low permeability matrix, sublimation could be diffusion limited. Gas molecules generated deep in the nucleus would take time to migrate to the surface. You'd get delayed outgassing, appearing long after peak heating. But that should still produce detectable gas, Popescu countered. Unless the gas recondenses before reaching the surface, which would require a very specific thermal gradient. The conversation spiraled through possibilities, each one plausible in isolation, each one requiring multiple assumptions when applied to 3 Atlas. It was the nature of frontier science. When observations outpaced understanding, explanations proliferated, and the only way to narrow the field was to gather more data. Which brought the discussion back to scheduling. La observation is confirmed for November 1st, Chandra announced. 6-hour window, multi-frequency setup. We'll cover 1 to 10 GHz, looking for any repeat of the park's transient. ALMA observation is scheduled for November 4th, Tanaka added. Submillimeter imaging should give us spatial resolution on thermal emission. We'll finally see if the heat distribution is uniform or structured. And Webb? Someone asked. Still waiting for DDT approval, Popescu said. Committee meets tomorrow. Notification by November 2nd, Doriki. 11 days post-detection, the grad student noted. If there was an outburst, it'll be long over. Maybe, Tanaka replied. Or maybe it's still happening. Delayed response, remember? A quiet laugh rippled through the room, tension easing slightly. Because delay, frustrating as it was, also meant opportunity. If 3I Atlas was responding slowly to solar heating, the response might still be unfolding. The best data might still be ahead, not behind. After the briefing, Chandra returned to his office and pulled up the Mars paper again, reading the methods section in detail. Torres and her team had used a technique called time-resolved spectroscopy, measuring mineral composition at multiple intervals after introducing water to Martian rock samples in a laboratory environment. The mineral signatures changed slowly, appearing in sequence as different chemical pathways activated. He wondered if a similar approach could be applied to 3I Atlas. Time-resolved thermal imaging. Sequential spectroscopy. Mapping how the object's properties evolved over days and weeks, looking for patterns in the sequence of changes. But that required continuous observation, or at least frequent snapshots. And the gaps in the observing schedule made continuity impossible. Still, the Mars paper offered something valuable: validation that delay was scientifically interesting. That extended response times weren't just observational inconveniences, but windows into process. That waiting, when done with the right instruments pointed at the right target, could reveal mechanisms that instant response would obscure. Delay wasn't the problem. It was the data. That afternoon, Chandra received an email from Dr. Lena Torres herself. She'd seen his name on the 3 Atlas observation reports posted to the IOU circulars and wanted to connect. "Your interstellar object and my Martian rocks might be distant cousins," she wrote. "Both showing that matter doesn't perform on command. Both teaching us to measure patience in weeks, not seconds. If you want to talk about delayed response chemistry, I'm happy to consult. We've learned a lot about diffusion-limited processes that might translate." Chandra replied immediately, scheduling a video call for the following week. Because the answer to 3 Atlas's mystery might not come from cometary science alone. It might come from geology, chemistry, material science, fields where delay was not anomalous but expected, where understanding meant mapping timescales rather than assuming instant equilibrium. The data doesn't rush. It waits. And sometimes, what waits is not an answer but a framework. A way of thinking about time and matter that makes delay not a barrier to understanding, but a path toward it. On Mars, water seeped through rock over weeks, rearranging minerals, leaving traces that appeared long after the wetting event. On 3 Atlas, heat soaked through ice over weeks, rearranging thermal distributions, leaving signatures that appeared long after perihelion. Both were obeying the same principle: diffusion takes time. The question was whether 3I Atlas's time was taking too long. And that question, like the object itself, receded into space at 23 kilometers per second, waiting for instruments to catch up, for our observation windows to open, for the slow machinery of science to point its full attention at the gap between heat and response. Chapter 6, November 3rd, 2025. The rotation that shifted after heating. Light curves, graphs of brightness over time, are one of the oldest tools in astronomy. Point a telescope at an object, measure how its brightness changes, and you can infer its rotation rate, its shape, sometimes even the distribution of bright and dark patches across its surface. For 3I Atlas, the light curve had been straightforward through perihelion. Regular oscillations with a period of approximately 8.3 hours, suggesting an elongated object tumbling end over end, reflecting variable amounts of sunlight as different faces rotated into view. The amplitude of the oscillation, about 0.3 magnitudes, indicated modest elongation, maybe 1.5 to 1 axis ratio, typical for small solar system bodies. Then, on November 3rd, the pattern changed. Dr. Alina Popescu noticed it first, while processing photometric data from the Subaru telescope observation on October 26. She'd been generating an updated light curve to check for any brightness changes associated with the thermal anomaly, expecting to see the same 8.3-hour period continuing. Instead, the period had lengthened to 8.47 hours, a difference of 10 minutes over a full rotation. Small, but measurable. Well outside the uncertainty of the photometric timing, Popescu ran the analysis twice, checking for processing errors. Then she pulled up earlier observations from October 14th, before perihelion, confirming the original period. 8.3 hours, stable across multiple nights of observation. The rotation had slowed. She called Dr. Ravi Chandra and Dr. Yuki Tanaka into her office, pulling the light curves onto her monitor. "Look at this," she said, overlaying the pre-perihelion and post-perihelion data. The curves matched in shape. Same amplitude, same brightness range, but the post-perihelion curve was stretched in time, the peaks and troughs arriving slightly later than predicted. 10-minute difference, Tanaka said, measuring the shift. Over 8 hours. That's a 2% change in rotation rate. Caused by what? Chandra asked. Momentum transfer, Popescu replied. Something accelerated or decelerated the rotation. Outgassing is the usual mechanism, gas jets acting like tiny thrusters, pushing against the object. But We haven't detected any outgassing, Tanaka pointed out. I know, Popescu said. Which is the problem. Rotation changes in comets were well documented. Comet Hartley, too, showed measurable spin-up during its 2010 apparition, attributed to asymmetric gas jets. Comet 67P exhibited complex rotational dynamics, mapped in detail by Rosetta, including torques from localized sublimation events. The physics was understood. Gas escaping from the surface carried momentum away, and if the emission wasn't perfectly symmetric, the net torque changed the rotation. But those comets had visible Kamai, active outgassing, spectral signatures of gas emission. 3 Atlas had none of those. Could it be delayed? Chandra suggested. Gas venting internally, not reaching the surface yet, but still transferring momentum through subsurface pressure? Tanaka pulled up a simulation. Internal gas flow can transfer momentum, but it'd be subtle. To change the rotation by 2%, you'd need, let me run the numbers. She typed quickly, pulling up equations for angular momentum transfer. Assuming uniform density 800 meter size, you'd need to vent about 5,000 kilograms of gas asymmetrically. And it'd have to be moving fast, at least 100 meters per second. That's a lot of gas for an object showing no visible coma, Popescu said. It is, Tanaka agreed. They sat in silence, staring at the light curves. The data was clean. The rotation change was real. The explanation was missing. Could be thermal cracking, suggested Dr. Marcus Delgado, joining the conversation via video call from a conference in Houston. Rocks and ice expand when heated, contract when cooled. If you get differential thermal stress, material can fracture, shift, redistribute mass. That'd change the moment of inertia, Tanaka noted. Could alter rotation without external torque. Popescu ran a quick calculation. To get a 2% rotation change from internal mass redistribution, you'd need to move, maybe 10% of the object's mass from the center toward the equator, or vice versa. That's not subtle, Chandra said. No, Popescu agreed. That's catastrophic. We'd see surface changes, brightness variations, shape deformation. Unless it's all internal, Delgado countered. Subsurface voids collapsing, ice layers shifting. We wouldn't see that from Earth unless it reached the surface. The explanations multiplied, each requiring processes that were possible but unobserved, plausible but unverified. It was the challenge of studying an object too distant to resolve spatially, too faint to observe continuously, too unique to compare against a statistical sample. Every measurement raised questions. Every question suggested observations. Every observation required telescope time that had to be negotiated, scheduled, executed. And 3I Atlas kept receding, growing fainter with each passing day, the window for detailed study narrowing like an aperture closing in slow motion. We need higher cadence photometry, Popescu said. If the rotation is changing, we need to track it night to night, not week to week. Catch any acceleration or deceleration in real time. I can reach out to the amateur community, Tanaka offered. There are networks of backyard observers with good photometric equipment. They can contribute data points between our major telescope runs. Do it, Popescu agreed. That evening, Tanaka sent out a call for observations via the American Association of Variable Star Observers and the European Astrophotography Network. Within hours, responses came from New Zealand, Australia, South America, observers with telescopes ranging from modest 15-centimeter refractors to serious 40-centimeter reflectors, all willing to spend cold November nights tracking a faint speck in Taurus, measuring its brightness, contributing to the collective effort to understand an object that defied easy understanding. The response was heartening, but even crowd-sourced photometry had limits. Weather gaps, moonlight interference. The simple fact that 3E Atlas was getting dimmer as it receded, dropping below the sensitivity threshold of smaller telescopes. By mid-November, only observatories with meter-class instruments would be able to detect it reliably. By early December, even those would struggle. The clock was running. On November 4th, Chandra presented the rotation change finding at the weekly team meeting, alongside the thermal data, the radio transient, the spectroscopic non-detections. The full picture was emerging, an object warming unusually, emitting radio waves transiently, rotating differently than it had before perihelion, all while showing no visible signs of the processes that should produce those changes. "Let's be clear about what we're saying," said Dr. Gerald Park, a senior scientist who'd been with JPL since the Voyager era and had a reputation for cutting through speculation with uncomfortable precision. "We're saying that 3 Atlas is responding to solar heating in ways that don't match our models. We're not saying the models are wrong. We're saying the object is different." "Different how?" someone asked. "That's the question," Park replied. "Different composition, different structure, different formation history. Interstellar objects aren't solar system objects. We've known that since Oumuamua. They've spent hundreds of thousands of years in interstellar space, bombarded by cosmic rays, never heated above a few Kelvin until they stumble into a star system. That's a different evolutionary path. Maybe that path produces properties we haven't accounted for." No. It was a reasonable framing, one that kept the discussion within the bounds of known physics, while acknowledging ignorance about interstellar environments. But it didn't explain the radio transient. It didn't explain why the rotation change occurred without visible outgassing. It didn't explain the sustained thermal emission exceeding model predictions. It explained that we didn't understand, which was not the same as understanding. "Next steps?" Park asked. "Vla observation completed last night," Chandra reported. "Data still processing, but preliminary look shows no repeat of the radio transient, no extended emission, just upper limits. Alma observation is tonight," Tanaka added. "Weather's good and chilly. We should get clean submillimeter maps." "WebDDT was approved," Popescu said, and a quiet murmur of approval rippled through the room. "Observation scheduled for November 7th, near infrared spectroscopy and imaging. We'll finally have spatial resolution at multiple wavelengths." 3 days, someone calculated. 3 days, Popescu confirmed. The meeting adjourned with assignments distributed, observation plans finalized, models queued for revision once new data arrived. The work continued because the work always continued. Delay was not paralysis. It was just delay. But privately, after the others had left, Park pulled Chandra aside in the hallway. "The rotation change bothers me more than the thermal anomaly," Park said quietly. "Thermal models have a lot of free parameters. Composition, porosity, albedo. Tweak those, and you can fit almost anything. But rotation is mechanical. Angular momentum is conserved. If it changed, something physical happened. And if that something left no visible trace, then either our observations are incomplete, or the process is subtle in ways we're not equipped to detect." "Or both," Chandra offered. "Or both," Park agreed. They stood together in the fluorescent-lit corridor, watching people pass with coffee cups and laptops, living their everyday lives while parsing data from an interstellar object millions of kilometers away. "The longer this goes on," Park said, "the more it feels less like we're studying a comet and more like we're studying a riddle." Chandra nodded. "Riddles usually have answers." "Eventually," Park said. "But sometimes the answer is that you were asking the wrong question." He walked away, leaving Chandra alone with that thought and the faint hum of HVAC systems circulating conditioned air through the building. The data doesn't rush. It waits. And waiting, Chandra was beginning to understand, was not passive anticipation. It was active uncertainty. The state of knowing that information was coming, but not knowing what that information would reveal. The gap between measurement and meaning, between observation and explanation. 3 Atlas's rotation had slowed by 2%. Momentum had been transferred without visible cause. The object was changing in ways that obeyed physics, but strained observation. And somewhere in that strain, in the space between what we measured and what we understood, an answer was forming. Slowly. Incrementally. Like a rotation period stretching across 8 hours, adding minutes we hadn't predicted, marking time in ways we were only beginning to recognize. Chapter 7. November 7th, 25, Starship, Schedules, and Silent Sile. while 3I, Atlas posed questions to planetary scientists. SpaceX posed challenges to mission planners 300 kilometers away at Kennedy Space Center. Starship Flight 27 was scheduled for November 9th. The massive rocket, 120 meters tall, capable of lifting 150 tons to low Earth orbit, stood on the launch pad at Boca Chica, Texas, awaiting final propellant loading and systems checks. It was the fifth orbital test flight of the year, part of an aggressive cadence aimed at proving the vehicle's reusability, refining its landing profile, and demonstrating capabilities that NASA would need for the Artemis program's lunar landers. Mission tempo was accelerating. Flights that once took months to prepare now launched within weeks of each other. Booster recovery. Rapid refurbishment. Refly. The model had worked for Falcon 9. Over 300 launches, an unprecedented launch rate for orbital-class vehicles. And now SpaceX was applying the same philosophy to Starship. But rapid cadence created scheduling density. Launch windows. Range availability. Tracking assets. When every week had a launch, conflicts emerged. Telescope observation time competed with range safety operations. Data downlink windows overlapped with propellant loading procedures. The infrastructure of spaceflight, designed for an era when launches were measured per year, strained under demand, measured per week. Dr. Marcus Delgado sat in a meeting room at JPL, participating in a multi-agency teleconference about deep space mission priorities for the 2026 fiscal year. Representatives from NASA headquarters, the Planetary Science Division, various JPL mission teams, and international partners filled the video grid. The topic: whether to fund a fast turnaround interceptor mission to 3I Atlas. Such a mission was technically possible. A small spacecraft, maybe 50 kilograms, launched on a Falcon Heavy, using a Venus gravity assist to catch up with the interstellar object by mid-2027. Fly within a few thousand kilometers. Return high-resolution images, spectra, particle measurements. Answer months questions that ground-based observations might struggle with for years. The proposal had been drafted 2 weeks earlier by a team at Johns Hopkins Applied Physics Lab, leveraging heritage from the New Horizons mission and the DART asteroid impact demonstrator. Fast turnaround. Modest budget. High scientific return. But modest in NASA terms still meant $300 million. And $300 million required budget allocation, proposal reviews, congressional approval, processes that took years, not weeks. "We appreciate the scientific value," said the NASA headquarters representative, a career administrator named Dr. Sandra Okafor, whose job was to translate science enthusiasm into budget reality. "But we're in the middle of a continuing resolution. Discretionary funding is frozen until February at the earliest. Any new start requires offsetting cuts elsewhere." "What about repurposing an existing mission?" someone suggested. "Redirect a spacecraft already in development?" "Everything's committed," Okafor replied. Psyche launched last year. Europa Clippers and Cruise. Dragonfly's in final integration for its 2027 launch. We don't have uncommitted assets sitting in clean rooms. "Could we partner internationally?" asked a representative from ESA, the European Space Agency. "Cost share the development. Fly instruments from multiple agencies." "Possibly," Okafor said. "But that adds coordination time. We'd need to align schedules, negotiate data sharing agreements, harmonize export controls. You're talking 12 months minimum just for the paperwork." Delgado listened, frustration building behind his professional calm. The conversation wasn't wrong. Budget processes existed for good reasons. International collaboration required negotiation. Spacecraft couldn't be built overnight. But 3I Atlas didn't care about budget cycles. By mid-2027, if a mission launched in 2026, the object would be approaching Jupiter's orbit, dimming rapidly, receding at velocities that made even fast spacecraft look slow. The window for interception was narrow, maybe 18 months, and that window was measured from now, not from when funding might be approved. "What if we go smaller?" Delgado suggested. CubeSat scale. 10 kilograms. Single instrument. Launch as a secondary payload on a commercial mission. Interesting, Okafor said. But you'd need a launch trajectory that happens to be going in the right direction. And secondary payloads don't choose their orbits, they ride along with the primary mission. Could we buy a dedicated launch? On what budget? The conversation circled, everyone contributing ideas, all of them crashing against the realities of funding timelines, technical readiness, launch availability. By the time the call ended 90 minutes later, no decisions had been made, no missions approved, no funding allocated. Just agreement to continue monitoring the situation and revisit at the next quarterly review. Delgado closed his laptop and sat in silence, staring at the blank screen. No interceptor mission. Which meant everything humanity would learn about 3I Atlas would come from telescopes on Earth and in near-Earth orbit, watching from millions of kilometers, inferring properties from reflected light and thermal glow, building understanding from photons that carried information but not touch, not proximity, not the ground truth that only in situ measurements could provide. It wasn't a failure. It was a choice, or rather, a non-choice, a decision deferred until circumstances allowed action, by which time the opportunity might have passed. This was how discoveries were lost. Not through incompetence or neglect, but through the slow friction of institutions moving at speeds mismatched to the phenomena they studied. Later that day, Delgado walked across the JPL campus to the Mission Control Center. Her teams monitored active spacecraft. Perseverance on Mars, Juno at Jupiter, New Horizons in the Kuiper Belt, Voyager 1 and 2 in interstellar space itself. Decades-old missions, still returning data, still pushing the boundaries of human knowledge billions of kilometers from Earth. He thought about the proposal that had gone to NASA in 2005 to send a probe to intercept on Oumuamua after its discovery in 2017. Not approved. Too speculative. By the time the object was discovered, it was already leaving, and no spacecraft could catch it. He thought about the proposals to send missions to Kuiper Belt objects, to interstellar precursor missions, to probes that would study the heliopause and the local interstellar medium. All valuable. All competing for the same limited budget. Somewhere in the calculus of scientific priorities, interstellar objects ranked high in fascination, but low in predictability. You couldn't plan a mission around something you didn't know would appear. And by the time it appeared, planning was too late. Unless you had infrastructure ready. Fast spacecraft in storage, waiting for targets. Launch vehicles available on short notice. Budgets allocated for rapid response. We didn't have that infrastructure. We had schedules and committees and review boards, all necessary, all rational, all too slow for objects moving at 23 kilometers per second away from the sun. That evening, Starship Flight 27 scrubbed due to a ground systems anomaly. The launch slipped to November 12th. 3 days. In the grand scheme of space exploration, 3 days was nothing. But it was another reminder that even the most aggressive launch cadences operated on human timelines, not cosmic ones. The data doesn't rush. It waits. But opportunities don't wait. They pass, marked by trajectory and velocity, by objects receding into regions where our instruments lose sensitivity, where photons grow sparse, where uncertainty expands faster than knowledge. On November 7th, the James Webb Space Telescope turned its gold-plated mirror toward 3 Atlas for the first time. 6.5 meters of beryllium, cooled to 40 Kelvin, optimized for infrared wavelengths, capable of spatial resolution that ground-based telescopes couldn't match. The observation lasted 4 hours. Near-infrared imaging at multiple wavelengths. Spectroscopy across the 1 to 5 micron range. Every photon counted, processed, calibrated, archived. The data wouldn't be fully analyzed for days. But preliminary images appeared on screens at JPL, within hours of the observation completing. And what they showed made everyone stop talking. 3 Atlas wasn't uniform. It had structure. The thermal glow wasn't smoothly distributed across the object's surface. It was concentrated in 2 regions near the equator, separated by roughly 120 degrees in longitude, each one warmer than surrounding areas by approximately 30 Kelvin. Hot spots. Localized. Persistent. Warmer than ambient, which meant heat was being generated, or concentrated, or redistributed in ways that created thermal heterogeneity across the surface. Comets had hot spots. Rosetta saw them on 67P, patches where sublimation was active, jets emerging from fissures, localized heating from solar exposure on steep slopes. But 3. Atlas had no visible coma. No jets. No spectral evidence of gas emission. Just heat. Concentrated. Anomalous. Dr. Yuki Tanaka pulled up the thermal map on the main display in the Situation Room. False color, red for warm, blue for cool. The two hot spots glowed prominently against the cooler background. Heat sources, she said quietly. Active. Post-perihelion. Could they be albedo features? Someone asked. Dark patches absorbing more sunlight? We checked, Dr. Alina Popescu replied, overlaying optical images. The hot spots don't correlate with brightness variations. They're not darker. They're just warmer. Subsurface volatile pockets venting internally, suggested Dr. Ravi Chandra. Maybe, Tanaka said. But if gas is being generated, where's it going? We don't see surface emissions. Silence filled the room as people stared at the image, at the two bright patches glowing against the dark, cold surface of an object that shouldn't be glowing at all. We'll know more after spectroscopy's processed, Popescu said. If there's compositional differences, if specific molecules are concentrated in the hotspots, that'd tell us whether it's thermal or chemical. When will spectroscopy be ready? Delgado asked. 48 hours, Popescu said. 2 days, Delgado calculated. 2 days, Popescu confirmed. The waiting continued. But now, the waiting had shape. Structure. Two thermal anomalies separated by 120 degrees, rotating with the object, persisting post-perihelion. Not random noise. Not observational artifact. Signal. And signal, by definition, carried information. The question was whether anyone would launch a mission to read it up close, or whether 3I Atlas would recede into memory. Another interstellar visitor documented from afar, its mysteries catalogued but not solved, its questions archived for future objects that might arrive decades hence, if we were ready, if we had infrastructure, if timing aligned. Institutional hesitation had become part of the story. And the story, like the object itself, continued to unfold, measured in days and observation windows, in budget cycles and committee meetings, in the gap between what we wanted to do and what we could do within systems designed for different timescales. The universe didn't wait for our administrative calendars, but it did wait for light to travel, for heat to diffuse, for rotation to slow by 2% over days of silent momentum transfer. And in that waiting, in that delay between heat and response, between discovery and action, the narrative of 3 Atlas accumulated detail, complexity, and questions that would outlast the object's observability. Some of those questions would be answered. Some would remain, archived in datasets, waiting for future scientists, with better instruments, faster spacecraft, and perhaps systems flexible enough to respond when the universe delivered surprises on its own schedule. Not deep research. Next, Chapter 8, November 11, 2025. Chemistry that should have appeared first. Spectroscopy is time travel for chemistry. When molecules absorb or emit light at specific wavelengths, they leave fingerprints, unique patterns of spectral lines that identify their presence as reliably as a barcode identifies a product. Point a spectrograph at a comet, and you can read its chemical composition from millions of kilometers away. Water, carbon monoxide, methane, ammonia, the building blocks of worlds rendered into light. But spectroscopy also reveals sequence. Because different molecules require different amounts of energy to become active, they appear in order. Low-energy volatiles sublimate first, at temperatures barely above absolute zero. High-energy species require more heat, emerging only when surfaces warm past critical thresholds. The sequence is predictable, written into the laws of thermodynamics, observed on every comet studied in detail, until 3E Atlas died. On November 11th, Dr. Alina Popescu sat in her office at JPL, staring at the processed spectroscopic data from the James Webb Space Telescope observation 4 days earlier. The spectrum stretched across her monitor in a landscape of peaks and valleys, each feature labeled with its molecular identity, each one a chemical messenger from an interstellar object 36 million kilometers away. But the order was wrong. She pulled up a reference spectrum from Comet 67P during its 2015 perihelion, laying it beside the Throi Atlas data. On 67P, the progression had been textbook. Carbon monoxide lines appeared first, detectable even when the nucleus was still cold. Then carbon dioxide. Then water vapor as surface temperatures climbed. Finally, complex organics, formaldehyde, methanol, hydrogen cyanide, emerging only during peak heating, when deep subsurface layers reached sublimation temperatures. A thermal cascade, each species appearing when its turn came. 3 Atlas showed water vapor. Strong lines at 27 microns, indicating significant HO emission toward Ti. But carbon monoxide, which should have appeared first, which required temperatures of only 25 Kelvin to sublimate, was barely detectable. Carbon dioxide, with an intermediate activation energy, was present but weak. And hydrogen cyanide, which required temperatures above 180 Kelvin, which should have been among the last species to emerge, was prominent. Stronger than cow, nearly as strong as water. The sequence was inverted. Popescu ran diagnostic checks on the data reduction pipeline. Calibration errors could produce spurious line ratios. Atmospheric contamination, though Webb operated in space, could theoretically introduce terrestrial signatures. Instrumental artifacts could mimic emission lines. Every check came back clean. The spectrum was real. She called Dr. Yuki Tanaka and Dr. Ravi Chandra into her office, pulling the comparison onto the large monitor mounted on the wall. "Look at the HCN line," Popescu said, highlighting the feature at 3 microns. "It's 3 times stronger than the CO line. That shouldn't happen. HCN is refractory. It's locked in organics, requires high temperatures to liberate. CO is volatile. It should dominate early outgassing." Tanaka leaned closer, examining the spectral features. Could it be abundance? Maybe 3I Atlas just has more HCN and less CO than solar system comets. Possible, Popescu acknowledged. Interstellar chemistry might be different. Cosmic ray processing over millions of years could alter volatile ratios. But that'd be composition, Chandra interjected. "This looks like activation sequence. We're not just seeing different amounts, we're seeing species appearing out of thermal order." Popescu nodded. "Exactly. If this were purely compositional, we'd still expect species to appear in energy order. Abundant or scarce, low activation molecules should show up before high activation molecules. But we're seeing the opposite." She pulled up a thermodynamic chart showing sublimation temperatures for common cometary volatiles. Carbon monoxide, 25 K methane, 30 K carbon dioxide, 80 K water ice, 160 K hydrogen cyanide, 180 kK. Then she overlaid the observed emission line strengths from 3I Atlas. The correlation was inverse. The highest energy species were strongest. The lowest energy species were weakest. "It's backwards," Tanaka said quietly. "It's backwards," Popescu confirmed. The room fell into silence, broken only by the hum of computers and the distant sound of someone's phone ringing in an adjacent office. Chemistry didn't work backwards. Thermodynamics didn't invert. Low-energy processes always preceded high-energy processes, unless something was selectively suppressing the low-energy pathways or enhancing the high-energy ones. Could there be a matrix effect? Chandra suggested. If Ki, O, and Ku are trapped in water ice, they might not sublimate until the water sublimates, even if they're volatile at lower temperatures. That's a known mechanism, Tanaka agreed. Trapped volatiles. We see it in lab studies of cometary ice analogs. But trapping should delay all the volatiles equally, not selectively suppress CO while allowing HCN. Unless the ice structure is different, Popescu said, thinking aloud. If 3I Atlas has a different crystallinity, different porosity. Maybe that affects diffusion rates. Small molecules like CO can escape through tiny pores. Larger molecules like HCN need bigger pathways, which only open when thermal expansion cracks the matrix. Chandra shook his head. But HCN is emerging strongly now, 2 weeks post-perihelion. If the malcracking was the mechanism, we'd expect it to peak during perihelion, not after. They were back to delay. Always back to delay. Events happening later than expected, processes unfolding out of sequence, a timeline that refused to match predictions. What if the chemistry itself is delayed? Tanaka proposed. Not just sublimation, but reaction. What if HCN isn't sublimating from pre-existing deposits? What if it's being formed now, through reactions between other species? Popescu considered. Cyanide formation from methane and ammonia? That requires UV radiation or heat. And catalysts. Which 3A Atlas had plenty of during perihelion, Tanaka noted. Solar UV was intense at 29 million kilometers. Surface temperatures hit 250 Kelvin or higher. If you had the right precursors in the right geometry, you could synthesize complex molecules through photochemistry or pyrolysis, Popescu finished, and those reactions might continue post-perihelion, driven by stored heat. It was speculative, but it was testable. If HCN was being actively synthesized rather than passively sublimated, the spectral line profiles would show subtle differences. Doppler shifts indicating molecular motion, line widths suggesting temperature or turbulence. Popescu zoomed into the HCN feature, examining its shape. The line was slightly broadened compared to thermal expectations. Not dramatically, but measurably. Consistent with molecules in motion, possibly ejected from discrete sources rather than evaporating uniformly. Could be production sites, she said. Localized regions where chemistry is active. Could be the hotspots, Chandra added, pulling up the Webb thermal map. 2 warm regions, separated by 120 degrees. If those are chemically active zones, they produce molecules out of the normal thermal sequence, Tanaka completed. Not sublimation-driven, but reaction-driven. The hypothesis crystallized. 3 Atlas wasn't just warming and cooling passively. It was chemically active, undergoing reactions that produced molecules in an order dictated not by volatility, but by reaction pathways. Heat from perihelion had triggered processes that continued post-perihelion, sustained by stored thermal energy or by exothermic reactions that released their own heat. Delayed chemistry. Not just delayed release, but delayed synthesis. It aligned with the Mars paper Dr. Lina Torres had published. Reactions that took weeks to complete, unfolding long after the initial energy input. Except Mars had liquid water facilitating aqueous chemistry. 3I Atlas had frozen ices and organic compounds undergoing. What? Pyrolysis? Photochemistry? Some process that transformed simple molecules into complex ones, out of sequence, out of order. We need to model this, Popescu said. Build a chemical kinetic simulation. Start with plausible precursors. Methane, ammonia, carbon oxides. Expose them to UV and heat. Track what molecules form and when. Now, I can reach out to the astrochemistry group at Leiden University, Chandra offered. They have models for interstellar ice chemistry. This is adjacent. Do it, Popescu agreed. That afternoon, Chandra drafted an email to Dr. Ewine van Dishuk, a leading astrochemist whose work on molecular cloud chemistry had defined the field. He attached the 3 Atlas spectral data, outlined the observed inversion in molecular appearance, and asked whether any known reaction networks could produce such a sequence. Van Dishuk replied within hours, "This is fascinating and strange. Normal cometary chemistry is sublimation-dominated. You just heat ice and release what's frozen inside. What you're describing sounds like processing. Active chemistry. We see this in laboratory experiments with interstellar ice analogues exposed to UV. Complex molecules form through radical recombination, often appearing after simpler species, depending on the reaction barriers. I'll run some simulations and get back to you." While waiting for modeling results, the JPL team reviewed the rest of the Webb spectroscopy. Beyond HCN, other anomalies appeared. Methanol was present but weak. Odd. because methanol usually formed readily in ice irradiation experiments. Formaldehyde was absent, despite being a common photochemistry product. Ammonia showed tentative detection, but the line was noisy, right at the edge of significance. Each molecule told a story, but the stories didn't cohere into a single narrative. It was like reading a book with pages out of order, some chapters missing, others repeated. Could we be seeing compositional layering? Suggested Dr. Marcus Delgado during the evening team meeting. Different depths in the nucleus releasing different molecules as heat penetrates inward? Possible, Tanaka replied. If 3I Atlas has an onion shell structure, outer layers rich in one set of volatiles, inner layers rich in others, then as thermal waves propagate inward, you'd get sequential release, but that should still follow energy order within each layer. Unless each layer has a different thermal history, Delgado countered. If the object formed in multiple accretion events, each layer might have different processing history, different chemistry. Popescu pulled up a diagram. So outer layer, ice is condensed in a cold molecular cloud, rich in Co and She. Middle layer, warmer accretion environment, more water and cone. Inner layer, processed by cosmic rays during interstellar transit, complex organics synthesized in situ. Complex organics synthesized in situ. And heat diffusing inward activates each layer in sequence, Chandra continued. But because each layer has different composition, the molecules released don't follow simple thermal order, they follow the layer structure. It was a model. One model among several. Testable in principle, difficult to confirm without spatial resolution, far beyond what Webb could provide. You'd need to resolve the object's surface at kilometer scales, map compositional variations, track emission sources across the rotation, which would require a spacecraft, an interceptor mission, close-up imaging, and mass spectrometry, which wasn't happening. The conversation circled back to observation strategy. ALMA had completed its submillimeter observation on November 4th. Data was still being processed. Additional Webb time was possible, but not guaranteed. DT slots were precious, allocated only when targets evolved unexpectedly. Ground-based spectroscopy could continue, tracking molecular emission over time, looking for changes in line ratios that would indicate evolving chemistry. But fundamentally, they were working with snapshots. Glimpses separated by days, capturing moments in a process unfolding over weeks. Trying to reconstruct a movie from a handful of stills. The data doesn't rush. It waits. And sometimes, what waits is coherence. The moment when disparate observations align into pattern, when anomalies resolve into mechanism, when chemistry that seems backwards reveals itself to be chemistry operating under different rules. That night, Popescu stayed late, reviewing the spectroscopic data one more time. She pulled up every cometary spectrum in the archive. Halley, Hyakutake, Hale-Bopp, Lovejoy, 67P, Wild 2, comparing line ratios, looking for any precedent, any hint that solar system CONS had ever shown similar inversions. None had. Every comet followed the same basic sequence. Volatiles first, refractories later. Simple molecules early, complex molecules late. 3I. Atlas was alone in its strangeness. She thought about Oumuamua, the first interstellar visitor, which had accelerated away from the sun without showing any cometary activity. No coma, no tail, just anomalous motion attributed to outgassing too faint to detect or to solar radiation pressure on an unusually shaped object. The debate still wasn't settled. Probably never would be, given how quickly Oumuamua had receded beyond observation. Twai Borisov, the second interstellar object, had behaved like a normal comet. Textbook outgassing, conventional chemistry, nothing anomalous except its hyperbolic orbit, marking it as a visitor from beyond. One strange, one normal. And now 3I Atlas, strange in different ways. Not accelerating anomalously, but warming anomalously. Not lacking chemistry, but showing chemistry out of order. The sample size was 3. The variance was high. The understanding was incomplete. But incomplete understanding was still progress. Because now, they knew what questions to ask. Not just what is it made of, but what processes is it undergoing. Not just how hot is it, but what is it doing with that heat? The shift was subtle, but profound. From treating 3I Atlas as an object to treating it as a system. Dynamic. Evolving. Responding to energy input through pathways that involve not just physics, but chemistry. Not just sublimation, but synthesis. Matter rearranging itself on timescales of weeks, writing chemical signatures into spectra that arrived 8 minutes later at Earth-based telescopes, filtered through atmospheres and instruments and analysis pipelines, emerging finally as graphs on screens where human minds tried to read meaning into molecular patterns. The delay between heat and response was also the delay between reaction and detection, between chemistry happening out there and understanding happening in here. And that understanding, like the chemistry itself, was still unfolding. On November 11th, 36 million kilometers from Earth, 3E Atlas rotated slowly through space, its surface modeled with warm zones where reactions continued, where molecules formed and reformed, where the thermal memory of perihelion drove processes that wouldn't finish for weeks yet. Hydrogen cyanide accumulated in dusty pores. Water vapor diffused through fractures. Carbon monoxide, if it existed, remained trapped in some matrix we couldn't model, released on some schedule we couldn't predict. The chemistry didn't rush. It waited for activation energies to be met, for catalysts to align, for temperatures to reach thresholds where bonds would break and reform. And far away in laboratories and offices scattered across Earth, scientists waited too. For more data, for better models, for the moment when observation and theory would converge, when the backwards chemistry would reveal itself to be forwards chemistry, seen from an unfamiliar angle. That moment hadn't arrived yet. But the data kept coming. The observations continued. The spectra accumulated like sedimentary layers, each one a record of molecular abundance at a specific moment, the full sequence building toward eventual understanding. Eventually, if the observations continued long enough, if the funding held, if 3I Atlas remained bright enough to study as it receded into the outer solar system, where photons grew scarce and every spectrum required hours of integration time. The race was against dimming, against distance, against the inexorable geometry of objects moving away. But chemistry was patient, and so, by necessity, were those who studied it. Chapter 9, November 15th, 2025, The Radio Quiet Zone. Radio silence had returned to 3 Atlas. After the single 11-minute transient detected by Parkes Observatory on October 26th, every subsequent radio observation had yielded nothing. The Very Large Array's 6-hour observation on November 1st, null detection. Follow-up observations by the Arecibo Replacement Facility in Puerto Rico. Nothing. Even coordinated multi-telescope campaigns, designed to cover wide frequency ranges simultaneously, detected only the faint thermal emission expected from a cold object in space, whisper-quiet blackbody radiation, not the anomalous broadband burst that had appeared 3 weeks earlier. The silence was not surprising. Transient radio sources rarely repeated on predictable schedules. Pulsars were the exception, their lighthouse beams sweeping past Earth with metronomic precision. But most astronomical radio transients, fast radio bursts, pulsar glitches, flare stars, appeared once and vanished, or repeated erratically on timescales of hours to years. Still, the absence gnawed at Dr. Ravi Chandra Dutt. The initial detection had been marginal but real. 3 sigma, above noise, spectrally smooth, spatially coincident with 3I Atlas, moving with the object across the sky. The odds of random alignment were 1 in 20,000. But one detection did not make a pattern. It made a question mark. On November 15th, Chandra stood in the valet control room in Socorro, New Mexico, watching data stream in from the array's 27 dishes spread across the desert. The observation was part of a 48-hour monitoring campaign, the longest continuous radio watch of 3I Atlas attempted so far. If the transient repeated on any timescale from minutes to days, this observation would catch it. 16 hours in, the screen showed flat noise. Dr. Yuki Tanaka joined him via video link from JPL data. Anything? Nothing, Chandra replied. Upper limits are good, We detect anything stronger than a tenth of the original transient. But there's no emission. Not even hints. Could it be directional? Tanaka suggested. If the source is beamed, maybe we're not in the beam anymore. Chandra had considered that. Radio emission could be anisotropic, concentrated in specific directions due to magnetic fields, geometric alignment, or relativistic beaming. If the October transient had been a narrow beam sweeping past Earth as 3N Atlas rotated, then subsequent observations might miss it simply because the geometry had changed. We need to know the rotation pole orientation, Chandra said. If the beam is aligned with the spin axis, we'd only see it when that axis points toward us. But we don't have pole position constrained well enough. Could the light curve help? Tanaka asked. Rotation period's 8.47 hours now. If we assume the original transient occurred during a specific rotational phase, we could predict when that phase repeats. Chandra pulled up the photometric data. The October 26th transient had occurred at, he checked the timestamps, approximately 3:47 UT. The object's rotational phase at that time, based on light curve fitting, was roughly 0.3, just past one of the brightness peaks. 8.47 hours later, the same rotational phase would recur. And again, 8.47 hours after that. If the emission was tied to surface features rotating into view, it should repeat with the rotation period. He calculated the predicted times. Next occurrence of the same rotational phase, November 15th, 12:14 UT. That was in 6 hours. We'll be watching, Chandra said. The VLA observation continued through the night. Chandra dozed fitfully in a chair, waking every hour to check the real-time data displays. The radio spectrum remained quiet, a nearly flat line punctuated only by faint interference, spikes from distant satellites and terrestrial sources, easily identified and filtered out. 12:14 UT came and went. No transient, no burst, just silence. Chandra recalculated, accounting for the rotation period change observed between October and November. Maybe the period was still shifting, making phase predictions inaccurate. He ran through different scenarios, period decelerating linearly, period changing erratically, multiple rotation axes precessing. None produced a clear prediction for when the transient might repeat. By the time the observation ended at 18:0 UT, on November 16th, 48 hours of data had been collected. The team would spend days processing it, searching for weak signals buried in noise, looking for any frequency-dependent features or temporal variations. But the preliminary answer was clear. Whatever produced the October transient wasn't producing it now, or wasn't producing it in ways we could detect from Earth. Back at JPL, Dr. Alina Popescu was exploring a different hypothesis. She'd been reviewing the geometry of the October transient, not just 3I Atlas's rotation, but Earth's position relative to the object, the solar wind conditions, the interplanetary magnetic field orientation. Because radio emission didn't occur in a vacuum. It occurred in the context of the solar system's electromagnetic environment. Charged particles from the sun, magnetic field lines draped across planetary orbits, cosmic rays threading through interplanetary space. All of it created a complex medium through which radio waves propagated. And sometimes, that medium mattered. Popescu pulled up a solar wind model for late October, overlaying it with 3I Atlas's trajectory. On October 26th, the object had been located in a region where the solar wind speed was relatively low, about 350 kilometers per second, and the magnetic field was in a away sector, pointing outward from the sun. By November 1st, when the valet observed and detected nothing, 3I Atlas had moved into a different sector, a toward region where the magnetic field pointed sunward. Solar wind speed had increased to 420 kilometers per second. Different, electromagnetic environment. Could the transient be solar wind interaction? Popescu proposed during the team meeting on November 17. If 3E Atlas is venting charged particles, ions, electrons, they'd interact with the solar wind. Under certain conditions that could produce radio emission. Like planetary auroras, Dr. Marcus Delgado noted. Jupiter's radio storms are driven by solar wind compression of its magnetosphere. Exactly, Popescu agreed. But 3I Atlas doesn't have a magnetosphere. It's too small, too weakly magnetized. Unless... She trailed off, thinking. Unless what? Tanaka prompted. Unless it's generating a transient magnetic field. Triboelectric charging in an expanding dust cloud could create localized fields. If that cloud then intersected the interplanetary magnetic field, you might get reconnection, particle acceleration, radio emission. Chandra considered. That'd explain the transient nature. The field would be temporary, lasting only as long as the dust cloud expanded. And it'd be geometry dependent, only producing emission when Earth was in the right position relative to the cloud and the interplanetary field. And it seemed foul. It's testable, Popescu continued. If this model's correct, we should see transients only when 3I in Atlas is in specific solar wind sectors, and when Earth's geometry allows detection. We can predict future favorable conditions and observe then. Tanaka pulled up a solar wind forecast. Next, favorable geometry based on your model, November 23rd. We'd need radio assets available. I'll submit a proposal, Chandra said. The hypothesis was speculative, built on a single data point and a lot of inference. But it was specific enough to be testable, which made it scientifically valuable. Better a wrong hypothesis that could be disproven than vague speculation that couldn't be evaluated. Still, the radio silence troubled Chandra more than he wanted to admit. Because radio transients, once detected, created expectation. The universe had spoken once, however faintly. Silence afterward felt less like absence, and more like withheld information. He thought about the WOW signal, the famous 1977 radio detection by the Big Ear telescope, a strong narrowband signal that appeared once, was never detected again, and remained unexplained nearly 50 years later. Not aliens, probably, but also not definitively explained by any natural source. Just a moment when the universe made a sound we couldn't interpret, then returned to silence. 3A. Atlas's transient wasn't as dramatic as the WOW signal, but it shared that quality of appearing once, refusing to repeat, leaving questions in its wake. Maybe every mystery began this way. A single anomalous data point. An observation that didn't quite fit, followed by efforts to replicate, to contextualize, to explain, and sometimes followed by silence. That evening, Chandra walked outside the VLA facility, into the New Mexico desert, where the sky stretched black and vast overhead, the Milky Way a river of light arcing horizon to horizon. The radio dishes stood silent around him, their white surfaces glowing faintly in starlight, their massive forms motionless, except for the slow tracking of distant cosmic sources. Somewhere up there, invisible and distant, 3 Atlas continued its journey, warming, cooling, rotating, outgassing molecules in backward sequences, radiating heat from localized zones, perhaps charging its dust with static electricity, perhaps creating transient magnetic fields, perhaps doing nothing at all except tumbling silently through the void while humans projected patterns onto its behavior. The data doesn't rush. It waits. But interpretation couldn't wait forever. At some point, observations had to congeal into conclusions, however tentative. At some point, the team would need to say, this is what we think is happening, based on what we've seen. They weren't there yet. Not on November 15th, when radio silence had extended for 3 weeks, when the single transient detection sat isolated in the dataset, like a lighthouse flash seen once in fog, never repeated. Not yet. But the observation windows were closing. 3 Atlas was 39 million kilometers from Earth now, receding at 23 kilometers per second. Its brightness had faded to magnitude 21.5, right at the threshold for ground-based spectroscopy. Radio detection limits would worsen as the object grew more distant, its faint emissions diluted by the inverse square of increasing distance. Soon, observation would become impossible. And the story, incomplete, puzzling, full of hints but lacking resolution, would end not with answers but with ellipses. The quiet zone would expand, swallowing the object, leaving only archived data and unanswered questions. Unless something changed, unless the transient repeated, unless one more observation, one more spectrum, One more thermal map revealed the pattern that tied everything together. Chandra stood in the desert dark, listening to the sound of wind across emptiness, feeling the enormity of the sky pressing down, and waited. For signal, for meaning, for the universe to speak again. The radio dishes waited too, their receivers tuned to silence, their data streams flowing clean and empty, documenting absence with the same precision they'd use to document presence. Because absence was data too. Silence was information. What didn't happen constrained possibility as surely as what did. And constraint, given time, could narrow the space of viable explanations until only one remained, or until funding ended and telescopes turned to other targets and 3 Atlas vanished into the outer solar system, its mysteries intact, its radio transient, real or artifact, meaningful or coincidence, preserved forever in archives as one of astronomy's small, unsolved puzzles. A whisper heard once. Never confirmed. Never explained. Just data, waiting for context that might never arrive. Chapter 10, November 19, 2025. Cassini's old data, new meaning. Sometimes understanding arrives not from new observations, but from recognizing what old observations meant all along. Dr. Yuki Tanaka discovered the connection by accident. She'd been searching through NASA's planetary data system, looking for any prior examples of delayed thermal responses in icy bodies, hoping to find precedent that might normalize 3 Atlas's behavior. Comet data. Kuiper belt object observations. Enceladus thermal maps. Anything showing heat persisting longer than standard models predicted. She found something else. A dataset from Cassini's composite infrared spectrometer, collected during a close flyby of Enceladus on November 27, 2005. The observation had targeted the moon's famous tiger stripes, the fractures near the South Pole that vented water vapor and organic compounds into space, creating one of Saturn's rings. The data had been published extensively. The geysers, the subsurface ocean, the possibility of life. Enceladus had become one of the solar system's most compelling targets. But, buried in the supplementary materials of a 2008 paper, Tanaka found a footnote about thermal lag in the tiger stripe regions. CERS had detected elevated temperatures persisting for weeks after tidal heating models predicted they should decline. The authors had noted it briefly, attributed it to complex subsurface thermal architecture, and moved on. The finding hadn't been significant enough to warrant detailed investigation. Enceladus had bigger mysteries to solve. Tanaka pulled the raw data and processed it with modern techniques. The thermal evolution curves looked familiar. Too familiar. Heat building up faster than predicted during tidal flexing. Cooling down slower than predicted afterward. Spatial heterogeneity. Warm zones that didn't correlate perfectly with predicted stress patterns. And a timescale. Thermal output remained elevated for approximately 40 to 60 days post-peak. Not identical to 3 Atlas. Enceladus was a moon with a subsurface ocean and active geology. 3 Atlas was a small interstellar object with no tidal forcing. The scales were different, the mechanisms were different, but the pattern rhymed. She called Dr. Ravichandra and Dr. Alina Popescu into her office. "Look at this," she said, displaying the Cassini data alongside 3 Atlas thermal curves. Both showed the same basic shape: faster rise, slower fall, sustained elevated emission long after peak energy input. Enceladus, Popescu read from the label. The tiger stripes. From 2005, Tanaka confirmed. They saw delayed thermal response, noted it. Didn't follow up because, well, Enceladus had an ocean and geysers to explain. The thermal lag was a detail. Chandra zoomed into the Enceladus data. What did they attribute it to? Subsurface insulation. Complex layering. Basically, heat diffusion through heterogeneous material. Standard explanations. Which are the same explanations we've been using for 3I Atlas, Popescu noted. Right, Tanaka said. But what if the explanations were incomplete then? And we're inheriting that incomplete framework now. The question hung in the air. Because scientific understanding was cumulative. Each generation built on previous findings, accepting earlier interpretations unless given strong reason to revisit them. The Enceladus thermal lag had been explained sufficiently for its context. No one had thought to dig deeper because there was no pressing need. But now, with 3I Atlas showing similar patterns, maybe there was. Do we know if anyone followed up on the Enceladus thermal lag? Chandra asked. Tanaka shook her head. Not that I can find. Cassini moved on to other targets. The 2008 paper came out, included the observation as a footnote, and that was it. 17 years ago, Popescu calculated. 17 years, Tanaka confirmed. Chandra leaned back, thinking. Okay, so we have two objects, completely different in almost every way, showing similar thermal behavior. What's the common factor? Porosity, Popescu suggested. Both Enceladus's tiger stripes and 3 Atlas are likely porous. Low thermal conductivity, high insulation. Volatiles, Tanaka added. Both have subsurface volatiles. Water ice on Enceladus, probably multiple volatile species on 3I Atlas. Phase change, Chandra continued. Both systems involve solid gas transitions. Sublimation, heat absorption, and release through phase change, not just conduction. They were identifying mechanisms, not causes. Ways that heat could move through matter slowly, creating the observed delays. But mechanisms were a step toward understanding. What if we model them the same way? Popescu proposed. Use the physics framework developed for Enceladus. Porous regolith, volatile rich subsurface, phase change thermodynamics, and apply it to 3 Atlas. See if the math works. Worth trying, Tanaka agreed. Over the next 3 days, the team built a thermal model incorporating lessons from Enceladus. Layered structure, a porous outer shell, a denser volatile-rich interior, distinct thermal conductivities for each layer. Phase change dynamics, heat absorbed during sublimation, released during recondensation, creating internal heat pipes that moved energy more efficiently than pure conduction. Surface heterogeneity, localized warm zones where fractures or compositional variations altered thermal properties. The model wasn't perfect. Enceladus had tidal heating continuously replenishing energy. 3A Atlas had a single pulse of solar heating at perihelion. Enceladus had liquid water and active tectonics. 3A Atlas had frozen volatiles and no obvious geological activity. But when they ran the simulation with parameters tuned to 3I Atlas's size, composition estimates, and solar heating profile, the output matched observations better than previous models. The thermal lag extended to the right timescale. The spatial distribution produced warm zones separated by cooler regions. The overall energy budget balanced without requiring exotic heat sources. It works, Popescu said, reviewing the model output. Not perfectly, but better than anything else we've tried. It works because we borrowed from Enceladus, Chandra noted. Which means either the physics is more universal than we thought, or we're overfitting. Or both, Tanaka said. The distinction mattered. Overfitting meant tweaking model parameters until they matched data without ensuring the parameters were physically realistic. Universal physics meant the same processes operated across wildly different environments, which would be profound, suggesting that thermal lag, phase change dynamics, and subsurface heat redistribution followed rules that transcended context. To distinguish between overfitting and universality required more data, more objects, more observations, which brought them back to the fundamental limitation. Sample size, 1 Enceladus, 1 thread in Atlas, isolated data points in the vast parameter space of possible thermal behaviors. We need more interstellar objects, Popescu said, voicing what everyone was thinking. We're getting about 1 every 2 years, Chandra replied. Oumuamua in 2017, Borisov in 2019, 3 Atlas now in 2025. Next one, maybe 2027 or 2028, if the detection rate holds. And each one is different, Tanaka added. Oumuamua was weird in one way. Borisov was normal. 3I Atlas is weird in another way. We're not building statistics. We're collecting anecdotes. It was a frustration inherent to studying rare phenomena. You couldn't design controlled experiments. You couldn't request specific targets. You had to take what the universe provided and do your best to understand it with incomplete information. But the Cassini connection offered something valuable. Validation that delayed thermal response was real, had been observed before, and could be studied systematically. It suggested that 3A Atlas, however unusual, wasn't violating physics. It was obeying physics in ways we'd glimpsed but not fully understood. That afternoon, Tanaka contacted Dr. Carolyn Porco, the imaging team leader for Cassini, who'd retired from active mission work but remained engaged with planetary science. She explained the 3I Atlas observations and the parallel with Enceladus's thermal data. Porco replied with enthusiasm, "I remember that footnote. We debated whether to investigate further, but mission time was precious, and the geysers were the headline. If I'd known it'd be relevant to interstellar objects 2 decades later, maybe we'd have dug deeper. That's the thing about data. It has a half-life of usefulness that extends far beyond the mission that collected it." None. She offered to consult, to connect Tanaka with other Cassini team members who might have insights. Within days, a small, informal working group had formed. Cassini veterans, 3 Atlas observers, thermal modelers, all collaborating to extract meaning from datasets separated by 20 years and 4 billion kilometers. The effort didn't produce immediate breakthroughs, but it produced context. A sense that delayed thermal response wasn't anomalous but underappreciated. That the tools to understand 3E Atlas existed, scattered across previous missions, waiting to be reassembled. The data doesn't rush. It waits. And sometimes, the data that waits is decades old, archived in digital repositories, its significance unrecognized until new observations give it new meaning. On November 19th, 3E Atlas was 41 million kilometers from Earth, its surface temperature finally declining in a pattern that matched the revised model, incorporating Enceladus-informed physics. The hotspots persisted but were fading. The spectroscopic inversions remained unexplained, but the thermal evolution, at least, was beginning to make sense. Understanding was accumulating in pieces. Not a sudden revelation, but a gradual assembly. Each observation adding a detail. Each model revision improving fit. Each connection to prior work expanding the framework. This was how science often progressed. Not through dramatic eureka moments, but through patient accretion. Observations layered like sediment. Interpretations refined like polished stone. Meaning emerging slowly from the noise. Tanaka stayed late that night, reading through old Cassini papers, looking for other overlooked details that might inform current mysteries. She found a 2010 paper on Titan's seasonal thermal lag, a 2014 study of Europa's subsurface heat distribution, a 2019 analysis of Triton's atmospheric response to solar heating during its long seasonal cycle. Delay everywhere. In every icy world, on every moon, in every environment where heat moved through insulating material and phase changes complicated simple conduction. The solar system had been teaching this lesson for decades. 3. Atlas was just the latest reminder. And the reminder came with urgency, because interstellar objects didn't linger. They passed through, offering brief windows for study, then vanished back into the dark. If we were going to learn from them, we had to learn quickly. But quick learning still required patience. The patience to wait for data, to wait for processing, to wait for models to converge on explanations that matched observation. Patience and urgency held in tension. The defining experience of studying objects that moved through space on cosmic timescales, while human attention operated on institutional timescales. Somewhere in that tension, understanding grew. Not complete, not final, but growing. Like heat diffusing through a comet's heart, spreading incrementally, reaching new layers, activating new processes, changing the system in ways that would only become apparent with time. The data waited. The scientists waited. And 3I Atlas, receding into the outer solar system, continued its slow thermal negotiation with the energy it had absorbed at perihelion, releasing that energy on a schedule written into its internal architecture, indifferent to whether anyone was watching. But people were watching and learning and recognizing in old data new patterns that had been there all along, waiting for the right context to reveal their significance. This is what discovery looked like. Not fireworks, but recognition. Not invention, but connection. The past informing the present. The present reshaping how we understood the past. And both converging toward a future where interstellar objects might not seem quite so strange, where delayed responses might be expected rather than anomalous, where patience was recognized not as a limitation but as a necessary tool for understanding matter in motion across the cosmos. Chapter 11, November 23, 2025, Alignment Odds Sec. Probability is the language science uses to measure surprise. When an event is likely, we call it expected. When unlikely, we call it interesting. When extraordinarily unlikely, we call it anomalous. And when an accumulation of independent unlikely events occurs together, we begin to ask whether they're truly independent, or whether some deeper connection makes them collectively more probable than their individual odds suggest. By November 23rd, 3 Atlas had accumulated a collection of unlikely events. Dr. Alina Popescu spent the morning calculating exactly how unlikely. She started with the radio transient. 1 detection in 48 hours of ALA monitoring, no repeats. Based on background transient rates from years of radio sky surveys, the odds of a random transient aligning with 3 Atlas during an observation window, approximately 1 in 20,000. Unlikely, but not impossible. The universe was large. Coincidences happened. Next, the thermal persistence. Post-perihelion heat retention, exceeding model predictions by sustained margins. She ran Monte Carlo simulations varying composition, porosity, and albedo within reasonable ranges. The fraction of parameter combinations that produced thermal curves matching observations, approximately 3%. 1 in 33. Again, unlikely, but within the realm of natural variation. Interstellar objects might have unusual properties. The spectroscopic inversion. Hydrogen cyanide, appearing stronger than carbon monoxide. High activation molecules preceding low activation molecules. She consulted with astrochemists who built reaction network models. The fraction of plausible chemistry scenarios producing the observed sequence, less than 5%. 1 in 20. The rotation change without visible outgassing. 2% spin down over 2 weeks, with no detected coma. She reviewed cometary dynamics literature. Examples of rotation changes without observed gas emission existed, but were rare. Maybe 5% of observed cases, and those typically involved much smaller changes. 1 in 20 again. Each event, individually, was improbable, but not extraordinary. Science was full of 3 sigma results, 1 in 20 occurrences, edge cases that pushed against model predictions without breaking them. But what were the odds of all 4 happening to the same object? If the events were independent, you multiplied the probabilities. 1 in 20,000 times 1 in 33 times 1 in 20 times 1 in 20. 1 in 528 million. Popescu stared at the number on her screen. 500 million to 1. She double-checked the calculation. Reviewed her assumptions. Each individual probability estimate was approximate, subject to uncertainties in background rates and model parameters. But even being generous with the error bars, even rounding every probability upward to make coincidence more likely, the combined odds remained extraordinary. 1 in several million, at minimum. She called Dr. Ravi Chandra and Dr. Yuki Tanaka into a conference room, projecting her calculations onto the wall display. These are the individual probabilities, she began, walking through each event. And this, she highlighted the final number, is the combined probability assuming independence. Chandra leaned forward. 500 million to 1. Give or take, Popescu confirmed. Probably not that extreme once you account for uncertainties. But even being very conservative, we're looking at odds of 1 in 10 million or worse. Tanaka crossed her arms, thinking. Which means either we've witnessed an extraordinarily rare coincidence, or the events aren't independent. Exactly, Popescu said. If there's a common cause, some physical process or structural property that makes all four anomalies more likely to occur together, then the combined probability would be much higher. What kind of common cause? Chandra asked. Popescu pulled up a diagram. Hypothesis. 3 Atlas has an unusual internal structure. Highly heterogeneous. Layered composition. Maybe a rocky core with an icy mantle, or a rubble pile with large voids. That structure affects everything. Thermal diffusion is slower and more complex, creating persistent hotspots. Chemical reactions are compartmentalized, creating spectroscopic inversions. Outgassing is internal rather than external, changing rotation without visible coma. And that same structure somehow concentrates electric charge or creates transient plasma pockets, producing radio emission. It was a unifying framework. One anomaly explaining multiple observations. Elegant in principle, but speculative in practice, because they had no direct evidence of 3 Atlas's internal structure. No seismic data. No ground-penetrating radar. No way to see inside the object and confirm the hypothesized heterogeneity. We're inferring structure from consequences, Tanaka noted. That's always risky. Agreed, Popescu said. But the alternative is accepting that we've observed a 500 million to 1 coincidence. And while that's possible, it's scientifically uncomfortable. The conversation turned to how such structure might form. Interstellar objects originated in other stellar systems, formed in protoplanetary disks with potentially different compositions, different temperatures, different dynamical environments than our solar system's formation zone. They were ejected through gravitational interactions, close encounters with giant planets, stellar flybys, dynamical instabilities. The ejection process itself might fracture the objects, creating internal heterogeneity. Then came millions of years in interstellar space. Cosmic ray bombardment, altering surface chemistry. Collisions with interstellar dust. Gradual loss of volatile through impacts or radiolysis. Each process potentially creating layering, variations in porosity, compositional gradients. By the time an interstellar object arrived in our solar system, it would be a palimpsest. Formation history overwritten by ejection history, overwritten by interstellar processing. Complex. Heterogeneous. Different from anything that spent its entire life in one stellar system. That could explain a lot, Chandra said. But it's also non-falsifiable with current observations. We can construct a story that fits the data, but we can't test it. Not directly, Popescu agreed. But we can make predictions. If heterogeneity is the cause, we should see continued thermal complexity as 3I Atlas cools. The warm spots should fade at different rates. Spectroscopy should show evolving molecular ratios as different internal regions activate and deactivate. Rotation might continue changing. Testable predictions, Tanaka noted. Good. What? And we can apply this framework to the next interstellar object, Popescu continued. If high heterogeneity is common in interstellar visitors, we should see similar multi-parameter anomalies. If 3I Atlas is unique, that tells us something different. The discussion shifted to statistical philosophy. When were coincidences too unlikely to accept? The field of statistics offered thresholds. 5 sigma significance for particle physics, 3 sigma for most astronomy, various standards across disciplines. But those thresholds apply to single measurements, not to combinations of marginally anomalous observations. There's a risk of multiple comparisons, Chandra warned. If you measure enough properties, some will be outliers by chance. You can't just multiply all the outlier probabilities and claim detection of something. True, Popescu acknowledged. But these aren't arbitrary properties. They're physically related. Thermal behavior, chemistry, rotation. They're all consequences of the object's response to solar heating. They're connected observables. Which doesn't prevent coincidence, Chandra countered. Just makes it slightly less likely. They were approaching the edge of what data could resolve. Science required skepticism, especially when confronting low-probability events. The history of astronomy was full of anomalies that seemed significant until better observations revealed mundane explanations. Apparent superluminal motion in quasars, explained by relativistic beaming. The Mars face, explained by lighting and resolution. The Pioneer anomaly, explained by thermal recoil forces. Most anomalies dissolved under scrutiny, but some didn't. Pulsars had been anomalous until their mechanism was understood. Fast radio bursts had seemed impossible until multiple detections confirmed their reality. Sometimes the unlikely event was real and meaningful. The question was how to tell the difference between an anomaly pointing to new physics and an anomaly pointing to measurement noise or coincidence. More data was the standard answer. More observations to confirm or refute. More objects to build statistics. But 3I Atlas wouldn't provide more data forever. It was dimming toward invisibility. And the next interstellar object might not arrive for years. What's our confidence level? Tanaka asked. What are we willing to claim based on these odds? Popescu considered. I'd say there's compelling evidence that 3I Atlas is behaving unusually, and that the collection of anomalies is unlikely to be coincidental. Probable cause: internal structural complexity that we can't directly observe, but that manifests across multiple observables. Confidence: moderate. Certainty: low. Sounds like a publishable result, Chandra said with a slight smile. Sounds like a debate waiting to happen, Popescu replied. Because publishing probability calculations would invite scrutiny. Other researchers would challenge the assumptions, recalculate using different background rates, argue about whether the events were truly independent. The paper would generate discussion, criticism, refinement, which was how science should work. But it was also exhausting. Still, the calculations mattered. They quantified the sense of strangeness that had been building since October, giving it mathematical structure. 500 million to 1. Even accounting for uncertainties, even acknowledging the risks of multiple comparisons, the combined improbability was striking. Something about 3 Atlas was genuinely unusual. Whether that unusualness pointed to exotic processes, or just to combinations of normal processes in atypical configurations, remained unclear. But the object had earned its anomaly status. The data supported that much. The data doesn't rush. It waits. But data alone didn't interpret itself. Numbers were mute. Until human minds assigned them meaning, contextualized them against background knowledge, judged whether they represented signal or noise. And that judgment always involved risk. The risk of seeing patterns in randomness. The risk of dismissing real signals as coincidence. The risk of building elaborate explanations for mundane events, or of ignoring profound events because they seem too unlikely to be real. Science navigated these risks through process, peer review, replication, accumulation of evidence across independent investigations. One team's 500 million to 1 calculation would be checked by others. Some would find higher probabilities, some lower. Eventually, consensus would emerge. Or wouldn't. Some mysteries remained mysteries, their probabilities debated, but never resolved, their explanations forever tentative. On November 23, 43 million kilometers from Earth, 3 Atlas rotated through space, indifferent to the calculations being performed in its name, unaware of the probabilities being assigned to its behavior. It warmed. It cooled. It emitted photons and molecules. It transferred momentum through mechanisms unseen. It did what physics allowed, obeying laws that operated the same everywhere, even if the combinations of processes created outcomes that seemed improbable from the perspective of limited observation. And humans watched, measured, calculated, trying to decide whether what they were seeing was extraordinary or merely unusual, whether understanding required new concepts or just better application of old ones. The answer, perhaps, was both. Because the universe was large enough to contain many unlikely things, and small enough that sometimes those unlikely things wandered close enough to be seen, measured, and argued over in conference rooms, where probability calculations glowed on wall displays and scientists debated what coincidence meant. 500 million to 1. still not impossible, but uncomfortable enough to demand explanation. Chapter 12, November 27, 2025. The debate inside the data rooms. Science is a conversation, often contentious, always necessary. On November 27th, researchers from JPL, international partners, and university collaborators convened for a virtual symposium dedicated entirely to 3 Atlas. The meeting had been organized hastily, just 1 week's notice, but attendance was high. Planetary scientists, astrochemists, radio astronomers, thermal modelers, all gathering in video conference windows, arranged like a mosaic of faces, each one representing years of expertise brought to bear on a single question. What is happening to 3 Atlas? Dr. Gerald Park, the senior JPL scientist, moderated. His white hair and deep-set eyes projected gravitas through the camera. We're here to argue, he began bluntly. Not about whether 3 Atlas is interesting, it clearly is, but about what the data actually tells us versus what we're inferring beyond the data. Let's keep it honest. The first presentation was Dr. Alina Popescu's probability analysis. She walked through each anomaly, each likelihood calculation, the cumulative odds. 500 million to 1 if events were independent. Much better odds if they shared a common cause. The pushback came immediately. Dr. Simon Reeves, an astronomer from the European Southern Observatory, raised his hand virtually. Alina, you're calculating these probabilities using background rates from surveys that aren't directly comparable. The radio transient rate, for example, you're using all-sky survey data and applying it to a single pointed observation. The denominators don't match. Popescu nodded. Fair point. I adjusted for observing time and sky coverage, but there's definitely uncertainty there. The exact number might be off by an order of magnitude in either direction. But even being generous, the combined odds are still millions to 1. Or thousands to 1, Reeves countered, which starts to approach the realm of improbable but observable in a large sample. We've discovered thousands of exoplanets, hundreds of asteroids, dozens of Kuiper belt objects. Occasionally, we'll see outliers. Except we don't have a large sample of interstellar objects, interjected Dr. Yuki Tanaka. We have 3. One was weird in one way, one was normal. And now one is weird in multiple ways. That's not a statistical distribution, that's individual cases. Dr. Lina Torres from Caltech, the Mars geochemist who'd consulted on delayed chemistry, joined in. I think we're focusing too much on improbability and not enough on mechanism. The question isn't how unlikely is this. It's what physical process could produce these observations. If we can identify a mechanism, the probability becomes irrelevant. Exactly, agreed Dr. Ravichandra. Which is why the heterogeneous structure hypothesis matters. If 3I Atlas has complex internal layering, rocky core, icy mantle, large voids, whatever, that one property affects thermal diffusion, chemical sequestration, rotational dynamics, potentially even charge distribution. Dr. Maizhao, a thermal modeler from Beijing Normal University, spoke up. I've been running simulations with high heterogeneity. You can get thermal persistence, yes, but matching all the observations requires very specific configurations. You need insulating layers here, conductive pathways there, volatile pockets at precise depths. It's not impossible, but it's fine-tuned. Fine-tuned meaning improbable? Park asked. Fine-tuned meaning we don't have enough constraints, Zhao clarified. There's a huge parameter space. You can fit almost anything if you allow enough free parameters. This was the eternal challenge of modeling, balancing fidelity to observations against the risk of overfitting. A model with 50 adjustable parameters could match any dataset perfectly, but it wouldn't be explaining, it'd be describing. True understanding required models with few parameters that still captured the essential physics. What about the spectroscopic inversion? Asked Dr. Ewan van Dishoek, joining from Leiden University. That's hard to explain with just thermal heterogeneity. Chemistry has activation barriers. You can't get high-energy products before low-energy products unless something's suppressing the low-energy pathways. Van Dyshoek pulled up molecular diagrams. I've run reaction networks. If carbon monoxide is trapped in a water-ice matrix, it can be suppressed. Meanwhile, if you have UV-irradiated organics on the surface, pyrolysis could produce HCN through entirely different pathways. So the inversion isn't mysterious. It's just multi-pathway chemistry in a heterogeneous environment. But we don't have evidence of that environment, Reeves pointed out. We're inventing structure to explain observations, then using the observations to justify the structure. It's circular. It's inference, Tanaka countered. We do it all the time in planetary science. We infer Enceladus has a subsurface ocean because of plume composition, not because we've drilled through the ice. We infer exoplanet atmospheres from transit spectra, not from direct sampling. Those are different, Reeves said. Enceladus's ocean explains multiple independent observations consistently. Exoplanet atmospheres have theoretical precedent. What's the precedent for 3I Atlas's behavior? Cassini data from Enceladus, Tanaka replied, pulling up the comparison she developed weeks earlier. Delayed thermal response. Same general pattern. It happened before. On a geologically active moon with tidal heating, Reeves noted. Not a small, inert comet. Comets aren't inert, Park interjected. They're dynamic systems. We've learned that from Rosetta, from Stardust, from every close-up mission. Expecting them to behave like inert rocks is the error, not finding that they don't. The debate continued, voices overlapping, arguments refined in real time. Some defended the heterogeneity hypothesis. Others insisted the observations could be explained by more mundane means, if observational uncertainties were properly accounted for. Still, others occupied a middle position. Something unusual was happening, but what exactly remained unresolved? Dr. Marcus Delgado, who'd been listening quietly, finally spoke. Maybe we're asking the wrong question. We keep debating whether 3I Atlas is anomalous. But anomalous relative to what? Relative to solar system comets, yes. But it's not a solar system comet. It's from somewhere else. Formed elsewhere, processed elsewhere. Why should it behave like objects that never left home? The comment shifted the tone subtly. Because Delgado was right. The baseline for comparison was fundamentally mismatched. Every model, every expectation was built on solar system experience. But the solar system was one data point in a galaxy of hundreds of billions of stars, each with potentially different planetary formation histories. So what you're saying, Park summarized, is that 3I Atlas might not be anomalous in the broader context. It's just our first good look at how other stellar systems build small bodies. Exactly, Delgado said. And if that's true, then the lesson isn't this object is weird. It's our models are parochial. The statement landed with weight. Because if true, it meant every interstellar visitor would challenge expectations. Each one would require model adjustments, new parameters, expanded frameworks. We'd be perpetually learning, never predicting, which was both humbling and exciting. Still leaves the radio transient unexplained, noted Dr. Colin Marsh, the park's astronomer who'd first detected it. Even with heterogeneous structure, even with delayed chemistry, I don't see a mechanism for broadband radio emission from a cold cometary nucleus. Unless it's not cold, suggested Popescu. The hotspots are 240 Kelvin. That's warm enough for some interesting chemistry. Warm enough for localized gas flow, dust lofting, maybe triboelectric charging. 240 K is not hot enough for plasma, Marsh countered. You need thousands of Kelvin for ionization sufficient to produce radio emission. Unless the plasma is transient, Chandra proposed. A brief discharge event. Lightning in a dusty outburst. That could produce broadband emission transiently without requiring sustained high temperatures. Maybe, Marsh said, unconvinced. But we didn't see an outburst optically. No brightness spike, no coma development, nothing coincident with the radio detection. Could have been below our detection threshold, Tanaka suggested. Small outbursts happen all the time on comets, too faint or too brief to catch. The conversation spiraled through mechanisms, each one plausible in isolation, each one straining against the constraints of what hadn't been observed alongside what had. Eventually, Park called for a summary. Where's the consensus? Silence for a moment. Then, Van Dishoek spoke. I think we agree that 3E Atlas is behaving in ways that solar system comets don't typically behave. Whether that's because it's intrinsically different, or because we're seeing a rare but natural combination of processes, is unresolved. I'd add, Delgado said, that we're limited by observation. The object is dim, distant, and receding. We're doing our best with the photons available, but we're missing huge amounts of information. Spatial resolution, continuous monitoring, in situ measurements, all absent. So what's the publishable conclusion? Park asked pragmatically. Popescu fielded that. I'd say 3A. Atlas exhibits multiple anomalies relative to solar system cometary behavior. Combined probability of these anomalies occurring coincidentally is low. Proposed explanation involves heterogeneous internal structure affecting thermal, chemical, and rotational evolution. Confirmation requires future observations of additional interstellar objects, and ideally, in situ missions. Basically, it's interesting. We don't fully understand it, more data needed. Reeves summarized with a wry smile. Welcome to science, Park replied. Laughter rippled through the video grid, tension easing. Because that was the reality. Most research ended not with definitive answers, but with refined questions and calls for future work. Progress was incremental. Understanding accumulated slowly. But the symposium had value beyond conclusions. It had aired assumptions, exposed weak points in arguments, identified where uncertainty lay, in model parameters, in observational limits, in theoretical frameworks. And it had built community, a network of researchers now invested in interstellar objects, ready to mobilize when the next one appeared. The data doesn't rush. It waits. And while data waited, people debated, refined models, planned observations, and prepared for futures that might arrive in months or years or decades. After the symposium ended, the participants dispersed back into their separate institutions, time zones, and projects. But the conversation continued in emails, in preprint servers, in journal submissions that would be reviewed, critiqued, revised, and eventually published. And in those publications, 3 Atlas would join the literature, a case study in delayed thermal response, in spectroscopic inversions, in the challenges of interpreting objects from other stellar systems with tools calibrated for our own. Not solved, but documented. Added to the collective understanding, increasing the baseline for the next object, the next mystery, the next opportunity to learn what matter did when it traveled between stars and came close enough to be seen. On November 27th, 44 million kilometers from Earth, 3E Atlas continued its journey, unaware of the debates conducted in its name, indifferent to whether humans called it anomalous or normal or anything else. It cooled slowly, releasing the sun's heat on schedules written into its structure. It rotated, carrying its warm spots through day and night cycles relative to distant stars. It emitted molecules synthesized through pathways not yet fully mapped, contributing faint spectral lines to data streams that would be archived, analyzed, and argued over for years. And it taught, through its silence and its strangeness, a lesson that would echo through future studies. The universe doesn't rush to explain itself. It presents observations. It's our task to build understanding from those observations, knowing that understanding will always be incomplete, always provisional, always waiting for the next piece of data to confirm or overturn what we thought we knew. That's not a failure of science. That's science working as intended. Questioning, testing, refining, never entirely certain, always learning. And sometimes, when the data aligned just right, when enough observations accumulated, when models matured and debates settled, understanding would emerge, not complete, but sufficient. Good enough to predict the next object. Robust enough to guide future missions. Reliable enough to build upon. But that understanding wasn't here yet. Not on November 27, 2025, when 3N Atlas remained a puzzle more than a solution, a question more than an answer. The waiting continued. Chapter 13, December 1st, 2025, Heat Without Urgency. By December 1st, something unexpected happened. 3 realized. The thermal output, which had been declining gradually through mid-November, leveled off. Not declining to zero as models predicted, but settling into a plateau. Sustained infrared emission at approximately 60% of peak intensity, holding steady day after day. Dr. Yuki Tanaka noticed it first in the updated ALMA observations. She'd been tracking the sub-millimeter flux, expecting to see exponential decay, the classic cooling curve of an object moving away from its heat source. Instead, the curve flattened into a horizontal line. She pulled up data from 3 independent instruments, ALMA in Chile, the sub-millimeter array in Hawaii, and long-wavelength observations from the Herschel Space Observatory archives, processed with new calibration techniques. All 3 showed the same pattern. Plateau. Persistence. A thermal equilibrium that shouldn't exist. It's not cooling anymore, Tanaka said to Dr. Ravi Chandra over video call. Or rather, it's cooling so slowly that it looks like equilibrium over our observation timescale. Chandra examined the data on his screen. 46 million kilometers from the sun now. Solar flux is down to about 600 watts per square meter. That's 1/3 what it received at perihelion. Thermal output should be dropping proportionally. But it's not, Tanaka confirmed. Which means, Chandra prompted, though he knew the answer would be speculative. Either there's an internal heat source we haven't accounted for, or the thermal inertia is so extreme that we're still seeing delayed release from perihelion heating 6 weeks ago. 6 weeks is a long time, Chandra noted. It is, Tanaka agreed. But we've been building models around heterogeneous structure, heat pipes, phase change buffering. Those mechanisms can extend thermal timescales significantly. Maybe more significantly than we realized. She pulled up the revised thermal model, incorporating lessons from Cassini's Enceladus data. The simulation showed heat soaking deep into a porous, volatile-rich interior during perihelion, then slowly working its way back out through layers of varying thermal conductivity. With the right combination of parameters, low conductivity outer shell, high porosity middle layer, volatile reservoirs at specific depths, the model could produce a plateau lasting weeks. But only if the parameters were pushed to the edge of plausibility. Are we fitting the data or explaining the physics? Chandra asked, voicing the question they'd both been dancing around for days. Maybe both, Tanaka replied. Or maybe neither. Maybe 3I Atlas is teaching us that the physics we know allows behaviors we haven't seen because we haven't looked at the right objects. Net. It was philosophical, but not wrong. Science operated at the boundary between knowledge and ignorance, constantly discovering that the universe was more complex, more variable, more creative with its possibilities than human imagination anticipated. No outburst, Chandra noted, reviewing optical observations. No sudden brightening, no new spectral lines, no dramatic changes, just heat without urgency, Tanaka said quietly, and the phrase stuck. Because that was what 3 in Atlas was demonstrating. Thermal patience. Not the explosive release of stored energy, not the dramatic flare of cometary outbursts, but sustained, measured emission. Energy leaving the system exactly as fast as some internal process allowed, no faster, governed by timescales beyond human impatience. Over the following days, the team monitored continuously. Optical photometry from amateur networks, infrared observations from ground-based telescopes, radio monitoring, still hoping for a repeat transient, spectroscopy, when telescope time allowed. Everything showed the same story. Stability. The object rotating steadily, its rotation period now firmly established at 8.47 hours. The hotspots visible in high-resolution, infrared imaging, still warm, still separated by roughly 120 degrees in longitude. Spectral lines showing water vapor and hydrogen cyanide, ratios unchanging, emission rates declining but not vanishing. It was, in a strange way, anticlimactic. After weeks of anomalies piling up, of each observation revealing new strangeness, the sudden stability felt almost disappointing. As if 3I Atlas had decided it was done being interesting. But stability was data too. It constrained models just as powerfully as changed it. Because if the object was releasing heat steadily without new energy input, that meant the heat reservoir was larger than predicted, or the release mechanism was slower, or both. It meant whatever processes governed thermal evolution operated on timescales of months, not weeks. Dr. Alina Popescu updated her probability calculations. The odds of an object maintaining elevated thermal output this long after perihelion, given standard cometary models, less than 1%. Add it to the list of improbabilities. Another factor to multiply into the cumulative odds, pushing the coincidence hypothesis further into implausibility. Unless, of course, standard cometary models were simply wrong for interstellar objects. Unless the baseline for normal was calibrated on the wrong sample. Unless everything they'd observed, thermal persistence, spectroscopic inversions, rotation changes, radio transients, and now prolonged plateaus, was normal for objects that spent hundreds of thousands of years in interstellar space before encountering a star. Sample size remained the crushing limitation. 3 interstellar objects observed. One behaved strangely, Oumuamua. One behaved normally, Borisov. One behaved strangely in different ways, 3I Atlas. From 3 data points you couldn't draw a distribution. You couldn't calculate a mean or a standard deviation. You could only collect case studies and hope future objects would clarify whether the strange ones were outliers or representatives. On December 3rd, Dr. Marcus Delgado received word that NASA's budget for fiscal year 2026 had been finalized. The Planetary Science Division's allocation increased by 3%, enough to maintain existing missions but not enough to fund new interstellar object response capabilities. No fast turnaround interceptor program. No pre-positioned spacecraft waiting for targets of opportunity. He'd expected the decision, but it still stung. Because 3E Atlas would be the 3rd missed opportunity in a row. Oumuamua had left before any mission could be proposed. Borisov had been observable but distant, and mission concepts hadn't progressed beyond preliminary studies. Now, 3I Atlas was receding, still bright enough for ground observations, but already too far for a rapid intercept mission, unless it launched within weeks, which it wouldn't. The next interstellar object, whenever it arrived, would face the same constraints: limited lead time, no pre-planned mission, institutional inertia too great to overcome within the narrow window of observability. We were, Delgado realized, building knowledge passively, waiting for the universe to deliver samples, then doing our best with telescopes and spectrographs and models, never quite getting close enough to touch, to measure in situ, to answer the questions that required proximity. It wasn't failure. It was the reality of constrained resources and vast distances. But it was frustrating nonetheless. That evening, Delgado walked through the JPL campus as the California winter sun set behind the San Gabriel Mountain. The air was cool and clear, the kind of evening that made Pasadena feel almost peaceful, despite the city sprawling below. He thought about Voyager 1 and 2, launched in 1977, now in interstellar space themselves, humanity's first emissaries to the realm beyond the sun's influence. Traveling outward at 3.6 astronomical units per year, they'd need 17,000 more years to reach the distance of the nearest star. We could send things out, but bringing things in or catching things passing through required either luck or infrastructure we didn't yet have. Maybe the 2030s would be different. Maybe Starship's promised low launch costs would enable missions unthinkable now. Maybe international collaboration would fund permanent monitoring networks, rapid response spacecraft, dedicated resources for studying interstellar visitors. Or maybe each object would remain a fleeting glimpse, a collection of photons and spectra, interpreted from afar and never quite understood. On December 1st, 46 million kilometers from Earth, and receding at 23 kilometers per second. 3. Atlas rotated through its thermal plateau, releasing heat without urgency, chemistry proceeding at its own pace, rotation steady despite invisible momentum transfers. It had no coma visible to amateur telescopes and backyard observatories. No tail streaming behind it, like the classical comets that had fascinated humans for millennia. It looked, to casual observation, like a faint star, magnitude 21.8 now, requiring serious equipment to detect it all. But to instruments sensitive enough to measure its infrared glow, to spectrographs that could parse its molecular emissions, to radio telescopes listening patiently for any repeat of that 11-minute whisper, it remained active, warm, chemically dynamic, still responding to energy absorbed 6 weeks earlier, still working through processes that unfolded on timescales dictated by physics, not by human schedules. The data doesn't rush. It waits. And so did the object. Releasing heat increment by increment, molecule by molecule, photon by photon, writing its story into the electromagnetic spectrum where patient observers could read it, interpret it, archive it for future scientists who might have better tools, clearer models, deeper understanding. The urgency that had characterized October and November, the sense that something dramatic might happen at any moment, had faded. Not because 3A Atlas had become less interesting, but because its form of interest had shifted from the explosive to the gradual, from the shocking to the persistent. It wasn't performing. It was simply being. Existing in its slowly evolving thermal state, governed by internal processes we could infer but not directly observe, following a cooling curve that defied our predictions but obeyed physics nonetheless. And perhaps that was the deepest lesson. That not everything needed to be dramatic to be meaningful. That patience, thermal patience, observational patience, interpretive patience, was not a constraint but a feature. That understanding arrived not always through revelation, but through steady accumulation. Heat without urgency, response without haste. The delay between cause and effect, between energy absorbed and energy released, between observation made and understanding achieved, stretched across weeks and kilometers, and the slow processing speed of human institutions, trying to match pace with human institutions. Cosmic phenomena. But the matching didn't need to be perfect. It just needed to be persistent. And so the observations continued. Ground-based photometry tracking rotation, infrared monitoring documenting the plateau, spectroscopy measuring molecular emission rates, radio listening for signals that might never repeat. Each observation added data to archives that would outlive the individual scientists collecting it. Each measurement refined models that would inform future studies. Each question raised would be inherited by the next generation of researchers, along with the tools and frameworks developed to address them. 3I Atlas would fade from direct observation by late December, dropping below the sensitivity threshold of all but the largest telescopes. By January, it would be effectively unobservable from Earth, lost in the glare of background sky, or simply too dim to distinguish from the millions of other faint objects populating the cosmos. But its data would remain. Processed, archived, published, reviewed, reanalyzed with future techniques, cited in papers about objects not yet discovered. The legacy of an interstellar visitor that passed close enough to be studied, but not close enough to be understood completely. That warmed and cooled on its own schedule. That taught through its patience what urgency alone could never reveal. On December 1st, the waiting continued. But it was not empty waiting. It was observation, documentation, the slow construction of knowledge from fragments of evidence scattered across wavelengths and time. And that, ultimately, was enough. Not everything needed answers immediately. Some questions could wait. Some mysteries could remain mysteries a while longer, preserved in data, awaiting the moment when context or technology or insight would finally render them comprehensible. 3I Atlas had given what it could give. The rest was up to time, and to those patient enough to let time do its work. Chapter 14. December 5th, 2025. What the delay taught us. 50 days after perihelion, 3 Atlas was 48 million kilometers from Earth, magnitude 22.1, requiring integration times measured in hours to extract useful spectra. The object had entered what planetary astronomers called the fade zone, that regime where observations became expensive in telescope time, where every data point required difficult trade-offs against other worthy targets, where the science return per hour of observation began to decline steeply. On December 5th, the International Collaboration Tracking 3 Atlas held its final scheduled observation meeting. Not because the object had stopped being interesting, but because the practical limits of ground-based astronomy had been reached. Future observations would be opportunistic rather than systematic, dependent on available telescope time, and whether anything dramatic happened to justify a renewed intensive monitoring. Dr. Gerald Park opened the meeting with a summary. We've documented an interstellar object through its closest approach to the Sun and tracked its thermal evolution for 7 weeks post-perihelion. The dataset is unprecedented for an interstellar visitor. Now comes the work of understanding what we've collected. He pulled up a timeline showing key observations. Perihelion, October 11. First thermal anomalies detected October 14. Radio transient, October 26. Spectroscopic inversion confirmed November 11th. Rotation change measured. Hotspots imaged. Thermal plateau reached December 1st. Each of these observations challenged our expectations, Park continued. Individually, they're interesting. Collectively, they define an object that doesn't behave like solar system comets. The question this meeting needs to address is, what did we learn? Dr. Yuki Tanaka began. We learned that thermal response is slower and more complex than standard models predict. Whether that's because 3I Atlas has unusual structure, unusual composition, or because our models are incomplete is still debate. But the observation stands. Heat persisted far longer than expected. We learned that chemistry can occur out of the expected sequence, added Dr. Ewan van Dishoek, joining remotely from Leiden. The spectroscopic data shows high activation molecules appearing before low activation molecules, suggesting either delayed release from matrix trapping or active synthesis through pathways we don't normally consider for cold cometary nuclei. Dr. Ravi Chandra contributed the radio perspective. We detected a transient emission that shouldn't occur on inactive cometary bodies. It hasn't repeated, which makes interpretation difficult, but the detection was real. That tells us interstellar objects might occasionally produce radio signatures, possibly through charge separation in dust clouds or other mechanisms we need to investigate further. No. Dr. Alina Popescu summarized the statistical analysis. The combination of anomalies is improbable if they're independent, suggesting a common underlying cause, most likely internal structural complexity that we can't directly observe, but that manifests across multiple observables. Dr. Marcus Delgado brought the mission perspective. We learned that our infrastructure for rapid response to interstellar visitors is inadequate. We missed close-up opportunities with Oumuamua, Borisov, and now 3 Atlas. That's not a criticism of individuals. It's a systemic issue. We need pre-positioned assets, pre-approved mission concepts, funding mechanisms that can activate quickly. The conversation turned reflective. What had 3 Atlas taught that transcended its specific anomalies? Patience, said Tanaka quietly, and the word resonated through the video conference. Because patience had been the defining requirement. Patience to wait for observation windows. Patience to let thermal processes unfold over weeks. Patience to accept that some questions wouldn't be answered within the observability window. Patience to build understanding incrementally rather than demanding immediate clarity. The universe operated on its own timescales. Solar heating took minutes. Surface warming took hours. Subsurface heat diffusion took days. Chemical reactions took weeks. Rotation changes accumulated over months. Observations required coordination across institutions and time zones and competing priorities that moved at administrative speeds measured in fiscal years. The delay between heat and response was not just a property of 3E Atlas. It was a property of the entire system. Object, observation, interpretation, understanding. We're trained to think of comets as dynamic, Park reflected. Outbursts, jets, rapidly changing comas. But 3I Atlas showed us another mode, slow evolution. Thermal memory, processes unfolding gradually without drama. It's more planetary than cometary in that sense, noted Dr. Lena Torres, the Mars geochemist. Planets respond slowly. Seasonal changes take years. Geological processes take millennia. Maybe interstellar objects, having spent so long in cold storage, operate on intermediate timescales, slower than typical comets, faster than planets. The analogy was imperfect, but evocative, because 3I Atlas did occupy a middle ground, larger than dust, smaller than planets, warmer than interstellar space, but colder than active comets, responding to solar heating but not explosively, changing but not chaotically. It was teaching us about a regime of thermal and chemical evolution that we'd had limited opportunity to study, a regime where delay dominated, where cause and effect were separated by timescales long enough to obscure their connection, where patience was not optional, but essential. "What about future objects?" asked Dr. Simon Reeves from ESO. "How do we apply what we've learned?" "Better models," Popescu replied. "We'll incorporate heterogeneous structure as a default assumption rather than an exotic possibility. We'll extend our thermal lag predictions to longer timescales. We'll look for spectroscopic inversions as potential indicators of active chemistry, rather than dismissing them as calibration errors." "Better observation strategies," Chandra added. "Multi-wavelength campaigns from the start. Radio monitoring, even when we don't expect emission. High-cadence photometry to catch transient events." "Better institutional readiness," Delgado emphasized. "Proposals pre-written, mission concepts pre-vetted, funding pathways identified, so when the next object arrives, we can move faster. And better recognition that anomalous might just mean from somewhere else." Tanaka concluded, "We need to stop being surprised that interstellar objects don't behave like solar system objects. They're samples from different formation environments, different stellar systems, different evolutionary histories. Of course they're different." And then, the meeting continued for another hour, turning to publication plans. Multiple papers were in progress. Thermal evolution analysis, spectroscopic results, radio transient characterization, probability calculations, structural modeling. They'd appear in journals over the coming months, undergo peer review, generate responses and rebuttals. The scientific conversation would outlast the observation window by years, but there was also a sense of closure. Not completion. The questions remained open, but ending. The intensive observation phase was concluding. 3I Atlas would continue its journey, but humanity's detailed scrutiny would fade, shifting to other targets, other mysteries, other objects arriving from the dark. That evening, after the meeting ended, Dr. Yuki Tanaka walked to the edge of the JPL campus, looking out over the lights of Los Angeles spreading to the horizon. Somewhere above, invisible beyond city glow and atmospheric haze, 3E Atlas was receding toward Jupiter's orbit, cooling slowly, its warm spots fading, its chemistry quieting, its rotation steady. She thought about what the object had taught her personally. Not just the science, though that was considerable, but the experience of studying something fundamentally unfamiliar, of building understanding in real time, with incomplete data, with models that kept breaking, with instruments stretched to their limits. It had been humbling and exhilarating, because this was what discovery felt like. Not the triumphant eureka of solved puzzles, but the ongoing negotiation with ignorance. The slow accumulation of observations that gradually, incrementally, narrowed the space of possibilities. The recognition that understanding was always provisional, always subject to revision with new data. And the acceptance that some things would remain uncertain. The radio transient might never be explained satisfactorily. The internal structure might never be confirmed. The exact chemistry producing the spectroscopic inversions might remain debated. That was okay. Science didn't require complete knowledge. It required honest accounting of what was known and unknown, testable hypotheses, and commitment to following evidence wherever it led. 3. Atlas had provided evidence. Abundant, complex, sometimes contradictory evidence. The interpretation would continue for years. But the evidence itself, archived, calibrated, publicly available, would remain. Future scientists could reanalyze it with better models, compare it to future interstellar objects, extract insights that the original observers missed. The data doesn't rush. It waits. And sometimes, what data teaches most is patience itself. The recognition that understanding arrives on its own schedule, not ours. That the universe will not hurry its revelations to match human expectations. That delay, between heat and response, between question and answer, between observation and comprehension, is not a barrier to knowledge, but a fundamental characteristic of how knowledge forms. On December 5, 2025, 54 days after an interstellar object designated 3I Atlas passed within 29 million kilometers of the Sun, the intensive observation campaign concluded. The object continued its journey, carrying its mysteries deeper into the solar system. The observers returned to other projects, carrying their insights forward into future work. And the delay, thermal, observational, interpretive, persisted, a gap measured not just in kilometers and days, but in the space between what we'd seen and what we'd understood. That gap would narrow with time. Models would improve. Future objects would provide context. The questions raised by 3I Atlas would inform how we studied the next interstellar visitor, and the next, building understanding across decades and objects until the strange became familiar and the anomalous became expected. This was the work. Not solving mysteries instantly, but living with them long enough for solutions to emerge. Not demanding answers immediately, but creating conditions, observations, models, collaborations, that would eventually produce answers. And in the meantime, accepting that delay was not failure. It was process. It was how matter responded to energy, how data transformed into understanding, how science, patient and persistent, gradually illuminated the dark. We searched for reaction. What we found was patience, written into matter itself. In the cold geometry of a rotating nucleus, heat diffused at centimeters per hour, building toward responses that wouldn't manifest for weeks. In porous ice and carbonaceous dust, volatiles migrated through tortuous pathways, released on schedules dictated by thermal architecture we couldn't see. In spectral lines arriving at Earth 8 minutes after emission, molecules told stories of chemistry unfolding out of sequence, governed by activation barriers and matrix trapping in processes we were only beginning to model. 3 Atlas didn't perform for us. It simply existed, responding to solar heating according to physics that operated the same everywhere, but manifested differently in matter that had spent hundreds of thousands of years between stars, shaped by formation environments we could only infer, modified by cosmic ray bombardment we couldn't directly measure, carrying properties that strained our models because our models were calibrated on objects that never left home. The delay between heat and response was not anomalous. It was fundamental. What was anomalous was our expectation that the universe should respond on human timescales. That cause and effect should be separated by intervals comfortable to institutional schedules. That understanding should arrive quickly enough to satisfy funding cycles and observation windows, and the impatient curiosity of minds adapted to immediate feedback. The universe doesn't rush, and in refusing to rush, it teaches. Not through lectures or equations written in the sky, but through the slow accumulation of observations that resist premature interpretation, through thermal curves that plateau when they should decline, through molecules appearing out of order, through radio whispers heard once and never repeated, through rotation periods that change without visible cause. Each observation was data. Together, they formed a portrait, incomplete, puzzling, but undeniably real, of an object responding to energy in ways we were only beginning to understand. By late December 2025, 3I Atlas had faded below the threshold of routine observation. Occasional measurements would continue. A dedicated team using the largest telescopes could still extract spectra through January, but the intensive monitoring had concluded. The object receded toward Jupiter's orbit at 23 kilometers per second, carrying its heat and its chemistry and its mysteries deeper into the solar system. In a few years, it would cross Saturn's orbit. In a decade, Uranus, eventually Neptune, and beyond into the Kuiper belt, cooling toward equilibrium with the cosmic microwave background, its brief encounter with the sun fading into thermal memory and then into quiescence. But its data would remain processed, archived, analyzed, reanalyzed, published in papers that would be cited for decades, compared it against future interstellar objects when they arrived, used to refine models that would predict behavior more accurately, constrain properties more tightly, narrow the space of viable explanations. Understanding would continue to grow, asymptotically approaching completeness, but never quite reaching it. Because that's how science worked. Not through sudden revelation, but through patient accumulation. Not through certainty, but through progressively refined approximation. We searched for answers in the gap between heat and response. What we found was a lesson in waiting, in trusting that the universe, given time, would reveal its processes. That matter, allowed to evolve at its own pace, would write its story into observables we could measure. That patience, thermal, observational, interpretive, was not a limitation but a tool, as essential to understanding as telescopes and spectrographs and computational models. The delay taught us what urgency never could, that some questions can only be answered slowly, that some mysteries require living with them through their full temporal arc. That understanding, like heat diffusing through a comet's heart, moves incrementally through human minds and institutions, activating insights one connection at a time, building toward comprehension that arrives not in a flash, but in layers. This is not science fiction. This is December 2025. This is an interstellar object, 48 million kilometers from Earth, cooling slowly, rotating steadily, carrying evidence of processes we glimpsed but didn't fully resolve. This is a team of scientists across continents and institutions, watching patiently, measuring carefully, debating rigorously, accepting that some questions would remain open when the observation window closed. This is the nature of discovery at the boundary of knowledge, where the unknown is vast and our tools are limited, and the universe presents its lessons on timescales that test our patience and challenge our expectations. We found no aliens in the data. No signals of intent, no artifacts of technology, no evidence of anything beyond natural processes operating in configurations we hadn't previously observed. But we found something equally profound. Complexity we hadn't expected, timescales we hadn't accounted for, and the recognition that the cosmos, in all its patience, was still teaching us how matter behaves when it travels between stars, and it travels between stars, encounters the warmth of a sun after millennia of cold. The delay between heat and response, measured in weeks, kilometers, photons crossing space at light speed, carrying information that would take months to interpret fully, measured in the gap between seeing and understanding, between question and answer, between urgency and patience. And in that gap, in that delay, in that space where understanding had not yet arrived, but was forming, gradually, incrementally, through observation and analysis, and debate, and time, the real lesson resided. Not everything needs to be fast to be meaningful. Not everything needs to be answered immediately to be valuable. Some knowledge arrives only to those willing to wait. And the universe, patient beyond measure, will wait with us. Until we're ready. Until we've built the tools and frameworks and institutional capacity to meet its revelations on their own terms. Until the next interstellar visitor arrives, and we apply what 3E Atlas taught us, and learn something new, and refine our questions again, spiraling ever closer to comprehension of how small bodies from other stars respond to our sun's heat. The data doesn't rush. It waits. And so do we. Not passively, not hopelessly, but actively, patiently, preparing for the next object, the next observation, the next opportunity to watch the universe demonstrate its processes and teach us, once again, that delay is not barrier, but data. This was 3I Atlas, the delay between heat and response. This was what it taught us. And the lesson, like the object itself, recedes now into the archives and the outer solar system, preserved in data and memory, waiting for the future to provide the context that will finally render its strangeness familiar. We searched for urgency. We found patience. And in that patience, written into matter, into observation, into the slow work of science itself, we found something worth knowing. The universe responds on its own schedule. Our task is to wait well, to observe carefully, and to recognize that understanding, when it arrives, incrementally, incompletely, but genuinely, is always worth the delay. This is not science fiction. This is December 2025. This is what the delay taught us. Thank you for watching. Please like, subscribe, and share your thoughts in the comments. Where are you listening from? What mysteries do you think 3 Atlas still holds? The data is public. The interpretation continues. And somewhere out there, the next interstellar visitor is already on its way. This is the universe teaching patience. This is science at the boundary of the known. This is the delay between heat and response.